and let's talk about winding up the term. Okay. Now, before I get into what we need to do, let me get into something, so before I forget it, something that you need to do, and that is do the student course evaluations. They were very, very, very late getting these opened, but they are open now. I don't know if it happened the week before Thanksgiving or the week of Thanksgiving, but sometime very recently they've opened these up, and so now you can do the student course evaluations. Now, Angelita, I can't remember the others of you who were in both classes. If you will, go back and do the one for the Physical Science 111 that you took the first mini term. Now, those who may have taken Physical Science 111 in the summer or even last spring, no, don't go back and do those, though we'd love to have you, but you just won't find yourself in those classes. Okay, but those who were in the first mini-term class, and if you were in other first mini-term classes, they did not have these open as far as I know then. They said it was a problem, guess what, with Banner. Everything seems to be some problem with Banner or with Blackboard or with some of these other things that they've instituted and make us use. So if you were in a first mini-term course this fall, do your student course evaluation for that course as well. So that's the thing that I want to ask y'all to do. And now let's talk about what we will be doing, which is also stuff for you to do too, for the rest of the term. Today we're starting in Chapter 8, Atoms and the Periodic Properties. Okay. We will go for our usual 2.5 hours or whatever's left of it, and then we'll have the first lab. I think that's lab 12. Okay. And that would be based on the PHET lab simulations. Okay, it's a pretty interesting one, sort of a good one to fiddle with. I think you'll enjoy it. Okay, then on Thursday, and it probably won't take us our full 2 hours. Sorry about that. I feel like I'm cheating you out of your tuition dollars. But after that, on Thursday, we'll probably come pretty close to finishing Chapter 8. Okay, and if we don't finish it, we will at least get far enough along that will be fine, and then we'll do the second lab in this chapter, and that will be lab 13, I believe it is. Now, lab 13 will require your books. I have a few things on the slides that'll probably help with that, so I'll have those open. But if you've got a book, get a hold of, or can get hold of a book, get hold of one for Thursday's lab, because that will be most helpful to have the book available for that. Okay, now, if we finish Chapter 8, and here comes somebody, but they blocked out the name so I can't see it. Oh, iPad 6, okay, is coming in. I don't know who this is. Do any of you know who iPad 6 is?
No, sir.
Okay, let me see if I can catch him when he or she gets a microphone. Yeah, they're in. iPad 6, could you let me know who you are? Oh, great. Okay, gotcha, Amaya. Okay. Otherwise running under the alias of iPad 6. Okay, so that's 5 students here, and that's what we've got so far. All right, Amaya, I was just talking about how we're going to wrap up the term, and the first thing I was mentioning is please do the student course evaluations. Okay, they were very, very, very late getting these open, but they did open them either the week before Thanksgiving or the week of Thanksgiving. I don't know which it was, but it was just recently they've gotten them open. So please do the student course evaluations. Now, you have some time until, if you want to wait until after finals are over or after you see your grades, you can do that. But please don't forget to do that. If you do put it off, don't forget to go back and do it. Okay. And I was also saying, if any of you were in a first mini-term course that you did not get to do the student course evaluations because they didn't have them open as far as I know, then you can go in and do your first mini-term courses as well. Okay. And please do. We need that. It's good information. All right. Secondly is how we're going to wrap up this course. And we're going to start chapter 8 today, atoms and periodic properties. We'll go for our normal 2.5 hours or whatever's left of it. And then at 5:45, we will stop the class and go to lab. Okay? The lab is out there under week 7, instructional materials. The PHET link is there, and also the lab sheet is there. And we will go through and do that lab. Probably won't take us the full 2 hours, but this one, if my memory's right, is a pretty fun lab. I think hopefully you'll get some reinforcing of some of the stuff we'll be talking about in class. Now this chapter, to me, is a heady chapter. It has lots of names, lots of things happening, lots of stuff going through, and it's easy to get things confused. And some of the stuff is could be a little confusing, but one of the things that you might find confusing when we go over it is what isotopes are, but that's what the lab will be doing. So hopefully it'll at least straighten out that part for you or clarify a little bit. So that's today's lab. Then on Thursday, I'm guessing we'll probably finish the chapter. I don't know that for sure. We've got next Tuesday that we can use to finish the chapter, but if we don't finish the chapter on Thursday, we've got Tuesday that we can do it. I'm not going to give you a lab on Tuesday because that would have you doing the lab, filling out the lab, doing that while you're doing your final exam. That's too much. Okay, so this week, these last 2 labs will be literally the last 2 labs. Okay, we will not do any past this week. 12 today, 13 tomorrow. On Thursday, and then if we do finish the chapter on Thursday, now did someone else come in? No, I don't think so. If we do finish the chapter on Thursday, I'll go on and send you post the test for chapter 8. Okay, if we don't finish it until, well, we'll see. We'll talk about that on Thursday. Then on Tuesday, it'll be a day to, if we have some stuff to finish in chapter 8, we'll finish it. Okay, it will also be a great day to ask questions on labs that you have turned. Okay, wait, time out. Research papers are due next Tuesday. I'd far prefer to have them today, tomorrow, Thursday, or Friday, or even over the weekend or Monday, than wait and turn them all in on Tuesday. That's a lot of grading right at the end, and that's going to be makes me not a happy camper anyway. So anyway, the sooner you can get your research papers in, the better. Okay, but they're not technically due until next Tuesday, but the sooner you can get them in, the better. Okay, now what I was saying is, if we finish everything else on Thursday, if we finish the chapter and do the lab, which we intend to do on Thursday, if we finish the chapter, I'll go on and post the chapter 8 test, so you can do that over the weekend if you choose. Okay, but then on the following Tuesday, that's a class day, if we haven't finished the chapter, we'll finish chapter 8. It won't take us long, but we'll finish chapter 8. If we have already finished, if we finish it by Thursday, then what Tuesday will be spent doing is I'll answer questions on any of the labs. Well, you'll turn in your research papers, hopefully before them. and that'll be a good time to turn in any past due labs, turn any past due tests. If you finish Chapter 8 tests, get that submitted. And if you have any questions on any of the labs, on any of the tests, now I won't give you the correct answers on the test. That's not the kind of questions I'm asking about. But if you have questions like, what is this question meaning? You know, if you're confused over wording and things like that, that's a good time to ask those questions. Now is a good time to ask those questions, but that will be, if we finish all the lecture material, then that will be what Tuesday will be, is a makeup day for you to get as many things done as possible, and I will go with you, answer any questions you have on quizzes, on labs, on tests, on whatever. And then on Thursday of that week, well, at the end of class on Tuesday, I'll post your final exam, and that will be due on Thursday. And Thursday, you can come to class if you want to, just to check in with me. You can come to turn anything. You can do whatever you want to on Thursday, okay? But that basically is, expect to have the test in by then. Now, are any of you graduating this term? And Amaya is. Okay. Amaya, for you then, I don't know what date. Did they indicate to you what day your grades have to be in? No, sir. They didn't. Okay. They were talking about it at the faculty meeting, and you know, I brought up, well, many term classes, we still have class on Tuesday and finals are Thursday. And they said, well, you know, they gave some song and dance. So if you need your grades in earlier, be sure to ask me and I'll go on and post the final earlier so you can get it done. So if you find out you have to have grades in whatever day it is, Monday, Tuesday, Wednesday of next week, I'll put the final out there so you can get that done. The final will not take you long. It's matching. I can't remember if it's 16 or 20 questions, something in that ballpark. It won't take you long. Get it in, and I'll try to get your grade out there early. It seems like somebody else in the class said they were graduating too, but I only got 5 people here, so I can't tell. Okay, any questions on how we're going to wind up the term? All right, if there's no questions, we're in Chapter 8, Atoms and Periodic Properties. This, by the way, if you notice at the top of that page, if you do have a book open, there's a little tab at the top that says Chemistry. So this is the chemistry part of chemistry and physics. The first chapter was science in general, so that included chemistry. But chapters 2, 3, 4, 6 were all basically physics type material, and this is basically chemistry type material. Though chemists are also concerned with heat and temperature. They're also concerned with energy. They're also concerned with many of the other things we talked about. But this is the chapter that is mostly chemistry, though you'll see a lot of physics in here as well. Those aren't completely separate fields. Okay, so Chapter 8, Atoms and Periodic Properties, page 205 in your text. If you've got the text, it would be 8-1 if you have the little book. Okay, here is, if I can get it to proceed here, here is the core concept, also on page 205. Different fields of study, physics, chemistry, and many others, have contributed to the development of the model of the atom. In fact, many of the people we'll name were physicists, as well as those that were purely chemists or fiddled in both fields. Okay, so different fields of study contributed to the development of the model of the atom. Now, that's not all we're going to do, but that's part of what the bulk of what we're looking at in this chapter. the model of the atom and how that fits into what properties materials have. Okay, so flipping the page to 8.1, atom atomic structure discovered. Now we'll go back. I think we've hit this guy before, but we're going to hit him again. The ancient Greeks had at least two different schools of thought on this. Okay, the first came from Democritus, an ancient Greek philosopher, and he had this concept: if you have a bar of iron, say, or anything, you broke it into two pieces, you still have two pieces of iron. You keep breaking the smaller piece into smaller and smaller and smaller pieces, and he said at some point, now this is just a thought experiment, at some point you're going to get down to the smallest piece of iron that you can have, and it's still called iron. Okay? He called that smallest particle of any material that is still that material, he called that an atom. And that comes from the Greek word meaning indivisible. Okay, so that's why what he came up with. Now this was 460 to 362 BC. Now that sounds like to me a pretty long lifespan. Okay, that was what, 98 years? Okay, wow. I didn't know folks lived that long back then, okay? But anyway, that was Democritus. However, in a few generations later, I don't know how many exactly, but along came the big three philosophers in Greek philosophy. I mean, they had many great philosophers, many great thinkers, but they had three in a row who really were outstanding and are still considered outstanding to this day. The first of these was Socrates, and y'all probably read and heard about Socrates. He was not that much on what they call natural philosophy. He did mostly head type philosophy, government, that kind of philosophy. However, I can't remember the order of these. One of these, Plato or Aristotle, was basically a student under Socrates, and he went on to do really great things and launched a little bit more into natural philosophy. And I think the last was Aristotle. I think Plato was in the middle and there Aristotle, but if it's vice versa, whichever. But Aristotle was the big wheel in natural philosophy. Okay, and boy, if Aristotle said it, for millennia people paid attention to it. They did not argue with Aristotle. But there, Plato and Aristotle both came up with the argument that matter is continuously and infinitely divisible. That there is no smallest piece, that you could keep dividing till the cows came home and you'd always have that material. Okay? And again, Aristotle missed the boat on this one. Democritus, like a generation or two or three before him, was absolutely right. Okay? There is some smallest piece. Now, could Democritus find it? No, they didn't have the technology for that. Can we see it? Not really. Somebody can, but okay, someone just came in, I think, but I can't see who it is. Let's see if I can get that to disappear. Okay, it starts with a D, so I'm guessing maybe Diana. Let's see, there it's finally. No, Daniel is here. So let me get Daniel into the class. Okay. All right. Now we're up to 6 students. Where, oh, where are my students today? Yep, we got 6. Let me make sure nobody else is in the waiting room. Nope, don't see anybody. Okay. Daniel, we're just beginning chapter 8. Okay. on somewhere along on page 208, 206 if you got a book, and that would be 8-2 if you've got the little book. Did you have a question? Okay. So, I'm sorry? Okay, maybe your microphone's on and you don't realize it. Okay, Daniel, you realize your microphone's on? Okay, good deal. Okay. Good. Okay. All right, so that was where things were from the ancient Greeks. Then along came John. Now this was, like you see here, more than 2 millennia later. Okay, well, maybe not from Plato and Aristotle. Well, it was pretty close to that, but definitely from Democritus it was. John Dalton, British scientist, chemist, reintroduced the atomic theory to explain chemical reactions. Now, a lot of things happen in between there, but most of them happen closer to the early 1800s. A few of them were happening later, but for literally centuries, no one argued with Aristotle or what his writings were. Now, they have this nice pretty picture here. I hate for it to go to waste. Well, let's see. Maybe it'll stay. No, well, nothing will happen. Let me do this. Nope, it went away. Let's look at this picture here. Now, this shows a nucleus. Now, there's some problems with this in that this nucleus and the objects in the nucleus are way too big for what they're representing. Okay? Now, their masses of all get out. I mean, just about the entire mass of that atom is in that tiny little nucleus. It just looks like it's a bigger nucleus than it really is. It is in reality incredibly tiny in volume, but enormous in mass. Okay? The reason for 2 colors here, one of these colors, I'm not sure which is supposed to be protons, and the other one's supposed to be neutrons. The nucleus is made up of positively charged protons, we'll call that the purple, and no charge on the neutrons, we'll call that the blue. Okay? Now, surrounding them are clouds of electrons. Now, here's the part that's probably completely misrepresenting things. Every one of these dots is not an electron. Not an electron, including these dots here, 3-dimensional dots, okay? Those are positions where the electrons might be. That's what those little dots are. Now, the sizes of the dots compared to the sizes of the protons and neutrons, the sizes of the electron, they're probably pretty close to reality, okay? Electrons have almost no discernible volume and incredibly small masses, like 1/10,000th the mass of a proton or a neutron. Okay, now, so these are just probabilities of where the electrons are. How many electrons are there? Well, in the inner shell there's 2 and only 2 in the gold sort of circle there. In the outer shell there are, now I'm just going to make a guess here, this looks like hydrogen, helium, lithium. It looks like beryllium to me. I don't know for sure. Beryllium has, if I'm reading this right, 4 protons and 4 neutrons. I'm pretty sure that's beryllium. That means there are 2 electrons somewhere in this outer shell and 2 electrons somewhere in the 2 electrons somewhere in the inner shell and 2 electrons somewhere in the outer shell. All these little dots don't represent electrons, they represent where that electron might be, okay? And these aren't very representative dots for that either, but at least it gives you an idea. Okay, so John Dalton didn't come up with this, but his discoveries moved people along this way. This came along much, 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 much later. Okay, here's how Dalton, here's a little history that went in between Aristotle way, way back there and Dalton. And this is shortly before Dalton. Another thing Aristotle said, well, there are only 4 elements. I think I've been through this before. Earth, wind, water, and fire. Okay? 3 of those made a singing group back when I was in college. Okay? Earth, wind, and fire. You may have heard of them. Okay? No. There was a group called Water. Okay? But Earth, Wind, and Fire was actually a singing group. And I think this is where they got their name. But that was Aristotle's view of nature. Those are the only 4 elements you have. Everything else is made up of one of those 4 elements in different combinations. Not one of them, different combinations of those elements. Well, along about the probably 1600s, 1700s, 1800s, or 16, 1700s, a band of people, or a group of people that later got the name alchemists, decided if those were the 4 elements, earth is cheap, water is almost free, wind or air is totally free, and fire is pretty cheap too. Okay, so if you could combine those 4 ingredients and get every other ingredient on the planet, that means somehow you could get those to come out and be, by mixing those together in different numbers and things like this, you could come out and get gold and silver, copper, platinum, all these precious metals from really cheap ingredients. So that spurred the alchemist into doing incredibly large amounts of research into how in the world these things go together. And basically they found out to keep from reinventing the wheel and making the same mistakes over and over and over, they were very good about recording their findings. And they kept careful notes and put different amounts of earth materials, different amounts of water, different amounts of fire, in other words, heating them, and doing things, and different amounts of air, blowing more air onto it, like the blacksmiths do when they tried everything they could and recorded it very nicely, and they were able to produce what we call a lot of chemical changes, chemical reactions by doing this. They never were able to produce gold or silver or platinum or copper or any of those other precious metals, diamond and things like this. They weren't able to do it, but boy, did they ever try. Okay? Now, John Dalton was one of the early chemists as opposed to alchemists. He studied and observed and went over this and found out that those things they had determined, the materials always went together in what they called the law of definite proportions. So in other words, if you were combining, say, oxygen with hydrogen, they always went with 1 gram of hydrogen for every 8 grams of oxygen. Always. Always. And other materials always followed what they called these law of definite proportions. Okay? The only way he could explain that was to say there are definite little particles out there that definitely go together in just certain patterns. So therefore, the idea of the smallest particle being there being called the atom. So that's why he brought back into play Democritus's atomic theory. Okay. Did either of them have it right? Well, no, not quite, but at least John Dalton was moving in the right direction. Now here was Dalton's model. I think I may have mentioned it to you before. his model because they thought definite proportions. And by the way, it seemed like always 1 unit of oxygen combined with 2 units of hydrogen to form water. Always. Okay, so he just pictured all these atoms that he was reviving that concept as having a certain number of hooks on them. Okay, for instance, if this is indeed beryllium here, beryllium had 2 hooks. It always combined with either one other thing with 2 hooks or 2 different things with 1 hook each. And that's what happened with oxygen. Oxygen had 2 hooks, hydrogen had 1 each, so 1 hydrogen on 1 hook, 1 on the other, and there you had water. Okay, use different things. Carbon always seemed to have 4 hooks, like I said, and sodium and potassium always had 1 hook. Calcium, magnesium always had 2 hooks. Chlorine always had 1 hook. Whoa, Daniel left and came back, I guess. But I've already got him here. So we still should be at 6 students. Let's see what we are at. Yep, 6 students. Let's make sure nobody else is in the waiting room. I don't see anybody, but things have gotten, well, I don't know why they're off-centered like that. Okay. So anyway, that was John Dalton's model of the atomic theory, that things were put together with hooks that satisfied his law of definite proportions. It satisfied the reason they always combined in certain ratios, so that seemed to work for him. But we've jumped the gun. There's a lot of difference space between Aristotle and Dalton, mostly shortly before Dalton. So let's go back and pick up some of that space if I could get the thing to advance. So here are the basic elements of Dalton's atomic theory. All matter is made up of indivisible atoms. That's sort of a redundancy there. Atoms means indivisible, so these cannot be broken down any smaller and still be that form of matter. We know today you can break atoms apart, but it always produces something different. But the smallest particle that a material can be in and still be that material is an atom. Now, here we get back into something we've talked about in the last several chapters. We have the macroscopic world and the microscopic world. In fact, the microscopic world is submicroscopic here. It's incredibly small. Now, atoms are the microscopic thing, the smallest indivisible particle that you can have. I don't think anyone has ever seen an atom. They've seen, say, where an atom wasn't in a lattice structure. They have seen effects of atoms, but I don't know if anyone has ever magnified anything great enough to actually see an atom. Okay? Now, the macroscopic idea here is an element. Now remember, Aristotle said there were only 4. By the time Dalton came along, they were convinced there were at least in the 20s and maybe in the 30s or 40s. I don't remember exactly when he came along, but a French guy named Lavoisier published the first reasonably accurate listing of elements, and I think he was in the upper 20s or so. He had a few things in there that weren't elements, but most of what he had in there were. And here's the concept in Dalton's atomic theory. All elements, if you have an element like iron or copper or beryllium or anything like that, it's made up of identical atoms. All the atoms in that are the same atoms. Now, if you have different elements, those different elements have atoms with different masses. Okay, and this explains the law of definite proportions. For instance, the mass of a carbon atom is usually right around 12. Okay, the mass of an oxygen atom is usually right around 16. The mass of a iron atom, it seems like that's up around 56 or so. I mean, mass of hydrogen is usually 1. Mass of helium, 4. So all the elements have atoms with different masses. Okay, I'm sorry, different elements have atoms with different masses. Definitely different masses. Okay, so that's the concept of pure materials, indivisible, same identical kind of atoms, they make elements. Now, many things in nature, and this is what the alchemists found out, were made up of combinations of atoms. 2, 3, 4 different kinds of atoms combined together in certain structures. These we call compounds. This is another macroscopic concept. Whereas elements were all made out of the same kind of atoms, compounds are made of atoms within specific integer ratios. That's part of the law of definite proportions, okay? That the chemical compounds are made of atoms in specific integer ratios. Water is made up of 2 hydrogens, 1 oxygen, always. Ammonia, 1 nitrogen, 3 hydrogens, okay? Carbon dioxide, 1 carbon, 2 oxygens, okay? That every chemical compound, and the chemical compounds are materials made up of more than one type of element, more than one element, more than one type of atom, okay? Now, atoms are neither created nor destroyed in chemical reactions. Even though heat is given off, nothing has burned, okay? Even though heat is absorbed like crazy, nothing is created nor destroyed. So atoms are constants of nature. They are neither created nor destroyed in chemical reactions. Now, later on, much later on, way past Dalton's time, we finally have nuclear reactions. Those are different from chemical reactions. Atoms are, I guess you would say, destroyed in nuclear reactions, and others are created, but the material product is still there, okay? So we're not going to get into that now. In chemical reactions, atoms are neither created nor destroyed. Okay, so don't know. Okay, this is sort of in order. Early in the 1800s was when Dalton was discovering what he discovered. Late in the 1800s, they finally were able to discover those little bitty, tiny, incredibly small electrons. Almost no volume that anyone's ever been able to detect, and just ever so tiny masses. About 1/10,000th the mass of a proton or electron, of a neutron, and protons and neutrons are pretty small particles themselves, so 1/10,000th of that is really, really small. Now, he performed these cathode ray experiments. Now, this is a picture of a cathode setup here. A cathode is actually the negative plate in a high voltage circuit, or any voltage circuit. That's called the cathode. The positive plate is the anode, okay? And you always have a tube. Now, in the tube, you try your best to evacuate all the air particles that you can. You want this to be as close to a pure vacuum as possible. Now, we can't produce a pure vacuum on Earth, but we can pump out as many of the molecules as we can possibly pump out. Okay? And then what you do, you put a high voltage here. So this is the negative side, that's the positive side. So the electrons. Now, at the time, they didn't know they were electrons. They called them cathode rays that went from the cathode toward the anode, from the negative to the positive. They could see or sense, they couldn't see them, but they could sense that there was motion down the tube like that, as long as much air had been pumped out as possible. If there's any air in there, you have arcing and sparking and nothing goes anywhere. Get that air out of the way and the cathode rays go down the tube. Okay? Now, he was doing these cathode ray experiments and he discovered these individual particles here that were made up. These cathode rays were actually individual particles, and they were negatively charged electrons. That's why they came off the negatively charged cathode and went toward the positively charged anode. They had to have been very strongly attracted, repelled by the cathode ray, attracted by the anode end of things, and therefore moved in that direction. So J.J. Thomson discovered the negatively charged electron. Now, again, it was so incredibly tiny, that there's no way he could measure the mass. He knew it had a charge, and here's the interesting, well, they haven't gotten there yet. We'll get to that interesting part later. He knew it had a fixed charge, and every one of those electrons had the same charge. Okay? If there were ever any more, they were always electrons that were bound together somehow, and they were always in integral multiples of that charge. Okay? You never can find half an electron or 3/4 of an electron. They always come in small whole numbers. Okay? Sometimes really big whole numbers too. But the best he could do was come up with the charge to mass ratio. That's all. He could not determine the mass. They were way too small to do that. He identified the electron as a fundamental particle that, and again they say, cannot be broken into anything smaller. Okay? Now, atoms can't be divided into anything smaller and still be that material, but an individual atom can be split into protons, neutrons, electrons, but they're no longer that particular matter. Okay? They're now just in the fundamental particles. Okay? So he identified an electron as a fundamental particle. An electron in iron is the same as an electron in silver, as the same as an electron in hydrogen or helium or oxygen. An electron is an electron is an electron, and they're individually fundamental particles. Okay. Now, here is basically how he did his experiment in a sort of simplified mean. Here was his negatively charged cathode, and he ran that through a ring that was positively charged, which basically tended to spread that band of electrons that was leaving the cathode. Okay? Now, then he put those two things at once here. He put it into an electric field. This is a horseshoe magnet, you might say, a U-shaped magnet. I don't know, doesn't matter which was the positive pole and which was the negative, north-seeking pole, south-seeking pole. It doesn't really matter, but one was north and one was south. So you had a very strong magnetic field going in one direction or the other here, because this was a permanent magnet, fixed magnet. Okay, he also sent this band of particles. Excuse me, I am having a lot of difficulty with stamina still. I haven't seen the results of my last blood work, but I can tell you now I'm still anemic. Okay, hold on just a minute. I find myself just needing a little bit of a boost every now and then. So not only do they put it in the presence of a strong magnetic field going this way between the north and south pole of that strong magnet, permanent magnet, but he also had charged plates here. One of these plates was charged positive and one was negative. But these were parallel like this, so that the magnetic field was this way, the electric field was this way, okay, going from the positive plate to the negative plate. The magnetic field going from the north pole to the south pole. You know how the field lines go. Okay. Now, then out here on this end, we had a detector, he had a detecting screen that the electrons, though he didn't know they were electrons, the cathode rays were striking this field here. Now, here are some things that he noted. Okay. Whatever was the positive plate here, it pulled the electrons up. The negative plate repelled them and pushed them up or down, whichever way they were. But not only that, the magnetic field made them bend in one direction or the other too. And we won't get into that part of it because that's a little complicated, but he found that his detecting string, that whatever, okay, now I need to correct something here. This positively charged ring here, the other thing it did was introduce positive charges. Negative charges were coming off the cathode. This introduced positive charges. Well, the positive and negative charges deflected in opposite directions, mostly depending on the electric field here. Positive charges bent away from the positive plate, whereas the negatively charged cathode rays bent, in the opposite direction. Okay. Now, the amount of deflection depended on the charge to mass ratio. That has something to do with momentum, and that's how he was able to come up with the charge to mass ratio. Could he get the mass out of this? No way. No way was there enough technology here, data here, anything else to get the actual charge. Nor the mass either, though he could approximate the mass, but he could get the charge to mass ratio, depending on how much deflection you had. Okay, so there was J.J. Thomson's cathode ray experiment, where he discovered these small negative charges, and they were the electrons. Okay, now that was late 1800s. Within probably 10 to 15 years, here was another character. And by the way, every one of these people is a legitimate paper topic. Okay? And what they did, their experiments, those would be legitimate paper topics. What they discovered, how they discovered it, those would be legitimate paper topics, or any other thing that you're interested in. Okay, so here came Robert Millikan, right around 1906 or so. He did an experiment that was called the Millikan oil drop experiments. What he did, he studied charged oil droplets. Now I'm going to try, okay, here's the picture. What he had was a sprayer, like some of you ladies may have, maybe you guys do. If you spray either perfume or cologne or something on, you atomize that by spraying across the top, and little bitty droplets of your, he was using oil, came and landed on the top of this plate. Now this plate here is charged positively. Okay? Now, most of those droplets landed on top of the plate. Only a few of them happened to land smack dab over the hole in the plate, and they fell through. Okay? This was held at a very large positive potential. The positive plate up here, negative plate here. So, he had a viewing scope here that he could watch these little droplets. Had light coming in from different angles. You could see the various droplets, and he could measure their movement. Now, a droplet that had no charge attached to it, in other words, no extra electrons on that droplet, they were going to fall just due to gravity. There was nothing to stop them. By the way, this was also pretty much in an evacuated space. You had as few air molecules in there as possible. So it was under a vacuum. If there was an electric charge on this, an electron, then the electric field would tend to push the electrons up because they would be repelled by the bottom plate, attracted by the top plate. If there was no charge or very little charge, gravity would be pulling down. So you have these two forces working against each other. Gravity was a constant, absolute constant, okay? But the electrostatic force was dependent on how many electrons were attached to that oil droplet. So if it went down just according to gravity, no charge was on it. If it went down a little bit slower, there was probably 1 or 2 or 3 electrons on it. If it came to rest here and kind of held steady, then you knew the force due to gravity was exactly equal to the force due to the electrostatic force upward. And we already knew what that was, Coulomb's law. So they knew the electrostatic force. Other particles got so many electrons on them, they actually moved upward against gravity. And then you could determine how many electrons were there. So he studied the charged oil droplets in an electric field, and the charge on the droplets were multiples of the electron charge. Okay? Now, since Thomson had a charge to mass ratio, and now you're able to isolate what the minimum multiple of that charge was, you now had the charge. Now you could calculate the mass. And here's the formula they use. Thomson's result was the charge to mass ratio, same as chapter 6. Excuse me, I need another. This is my 4th class of the day. I'm just running out of gas. The charge to mass ratio was 1.7584, you don't need to know the number, times 10 to the, I think that's 11. This is pretty poor print here, but I believe that's what that was. Let me go over and see if I can find that. Yeah, 10 to the 11th. Coulombs per kilogram. Whoa! Okay, that's a lot of coulombs for a kilogram's a huge mass, so that would be expected to be a large number of coulombs. Millikan's result gave them the charge. Okay, the charge on the droplet, the minimum charge was 1.60 times 10 to the minus 19th coulomb is the electron charge, and then the mass then would be, put Q up here, and this here, so the Q divided by this is equal to M. Multiply both sides by M, divide both sides by this number here, and that gave the mass of electron. Oh my goodness, look at that mass. 9.11 times 10 to the minus 31 kilograms. It would take me a long time to write 30 zeros there, okay? You would need a 0 point and then 30 zeros before you got to 9.11, 911, okay? That's an incredibly small mass. No wonder no one's ever put one of those on the scale. So now with the combination of Thomson's, J.J. Thomson's charge to mass ratio and Robert Millikan's determination of charge, then you are able to come up with an approximate mass for an electron. No one can ever put one on a scale, but you can come up with the approximate mass. Okay, so here are the early models of the electron. First, Dalton said, just like Democritus had said millennia earlier, that atoms were indivisible. Okay, Thomson and Millikan, the combination of their two experiments, said that the electron mass is incredibly small with absolutely no measurable volume. No one could detect what volume those tiny little particles took up. So what was the nature of the atom's positive charge? They did not know. Okay, now the same Thomson, J.J. Thomson here, came up with a proposal, and this is just a model. Remember, Dalton's model had hooks on the my wiring is all tangled up here. Okay, had hooks on the atoms. They weren't really hooks, but that was his model. Okay, well, J.J. Thomson had a model like this. He must have liked to eat like I do. He called it the plum pudding model. Now, what does he mean by that? Well, in a plum pudding, I don't know if I've ever had plum pudding, but think of raisin bread. That to me is a better model, but it doesn't sound as good. Okay, in raisin bread, you have the fabric of the bread all around here and the raisins scattered in various places inside the loaf. Okay, well, plum pudding must be the same way. You have the bulk of the pudding there, and then you have the little pieces of plum scattered throughout the mass of that pudding. So he was picturing the electrons as these little bitty pieces of plums or raisins in a blob of positively charged matter, like raisins in a plum pudding. He calls it raisins now rather than plum. I don't know. I don't know why he used mixed terms there. Okay, so little bitty things mixed in there. And that was his model. And that seemed to fit. Okay, there were definitely had to be positive charges. They would be attracted to the negative charges. Why wouldn't they be like this? Okay, why wouldn't they? Okay, well, along came Ernest Rutherford, just 1 year approximately after Millikan. Okay, and Ernest Rutherford, another British scientist. The British were really doing great guns here. I mean, John Dalton, British. Of course, some of the characters weren't that we haven't said, but I think J.J. Thomson was British. You know, most of these were British characters here. Okay, here came Ernest Rutherford. So he decided if indeed the positive charges were like the pudding and the plum pudding, and the electrons were just scattered throughout that material, then if he took, now one really neat thing about gold is gold is incredibly malleable, okay? Which means you can roll it into sheets just as thin as you can imagine, okay? Picture aluminum foil, okay? Aluminum foil is rolls of aluminum, okay? But it's pretty thick, especially the heavy duty stuff. But the lighter stuff gets a lot lighter, okay? Yeah. Well, gold foil, I mean, is so incredibly thin, okay, that, in fact, I don't know if you've ever seen it. Have you ever seen these picture frames that look like the frames are gold, but when you get a closer look, you see they're really wood, but they've taken this, they sometimes call it gold leaf, and just rub it onto the wood, and it attaches to the wood. And it's so thin, and it makes it look like the whole thing is gold, where in reality it's just a gold coating on top of wood or some other metal. Well, he took some of that really thin gold foil, like gold leaf or something, and had it very, very thin. Now, he didn't know, but he was figuring that was only a few atoms thick, okay? Now, he had no way of knowing how many atoms thick it was, but he knew it was a few atoms thick because it was very, very, very thin. Okay? Now, by this time they had discovered alpha particles. Now, what are alpha particles? They're basically the nucleus of helium atoms. In other words, you strip off the electrons of helium. Helium has 2 protons, 2 neutrons, and 2 electrons. Okay, we'll see that a little bit later too in today's lab. Okay, so therefore, it's if you strip off the electrons, that's a +2 charge, because you've lost the 2 electrons, so you have the 2 positive charges from the protons, and neutrons have no charges. So these are not big, but compared to electrons, they're incredibly massive, okay? These are called alpha particles. They're positively charged, whereas electrons are negatively charged. These are enormous masses, whereas electrons have incredibly small masses. So what he was going to do is fire these alpha particles off the gold foil, figuring that most of that plum pudding there is made up of positive charge, so if it hits the foil, it's going to get bounced backward, because like charges repel each other, and those alpha particles are totally positive, and most of the plum pudding is totally positive. So he was expecting to see significant deflection off the gold foil, so he set up his screen on the front side of the foil to measure what reflected and deflected alpha particles were going to be called. He found almost none. Almost none. So he put his screen in the back and found out most of those alpha particles went right through the gold foil. Absolutely through it, as if there was no plum pudding there. What is going on here? Except most went through. A few were scattered at enormously large angles. Very few, but a few were. Most of them went right through as if they never encountered any positive charge at all. But the few that were scattered at large angles, they obviously hit a positive charge. What is his conclusion? That an atom's positive charge resides not in a mass of plum pudding or the dough in a raisin bread, but in an incredibly small but incredibly massive nucleus. Now, those sound like two wrong words, that they contradict each other. Small meaning small in volume, massive meaning very massive in, if you'll pardon it, weight, but it's really mass, okay? Incredibly large mass, incredibly small volume, okay? Much later, those positive charges were identified as protons. Okay? And it may have been Rutherford that did that. Also, much later, like 25 years later, James Chadwick, another British physicist, chemist, also discovered the neutral neutrons that were also in the nucleus. Okay? The neutral and neutrons, they sound alike because that's what they are. They're neutral. The nucleus sounds like it too, but that doesn't have the E in it. That's just the core. So that then over about 35 years, something like that, they discovered the three main parts of any atom. Electrons, incredibly tiny, but with a fixed negative charge, floating around in space around an incredibly dense, massive, but incredibly small nucleus. And in that nucleus were your positive charges, later called protons, and later they discovered neutral charges, no charge at all, and they were called neutrons. Okay, so that's how the nucleus of the atom was discovered, really by accident. Okay, Rutherford was set up to measure something else, and when he couldn't measure that, he turned it around and found out what was really going on. Now here basically is his final setup here. These were the radioactive alpha source, alpha particles coming out of here, hitting the gold foil here, very, very, very thin gold foil. Most of those alpha particles, which are totally positive charged, total positive, no negatives in them at all, they were going right through and banging somewhere back here. A few, and very few, got bounced back this way, which is where he thought they were going to land initially. They didn't. Most of them came right through here. Now, what is this detecting screen? It's light flashes, and they had photosensors, and they were able to determine where most of the collisions occurred then. Okay, so that was Rutherford's experiment that helped discover the nucleus of an atom. Now, here is the conceptual view of what was going on there. Rather than the bulk of this being positive charge with just a few little electrons scattered in it, what we really had was an electron cloud which had almost no matter at all in it, and all the matter was situated in these tiny little nuclei. So when these alpha particles that were positively charged, basically nucleus of helium atom, though they didn't know that's what they were at the time, they just had an alpha source and they used it. They knew they were double positive charges, fired it through, most of them went right on through because they were not at all bothered by that electron cloud. But only occasionally and very rarely did they happen to smack right into a nucleus, and then they were deflected backward at a very, very large angle. So the bulk of your alpha particles landed on the screen here, and very few of them made it back here somewhere. And that's where he originally thought they were all going to be. Almost none of them, just a few, and those were significant, those few, and that's because they were hitting the actually tiny, really tiny little nucleus and being deflected back because they were light charges. Those going through the electron cloud zoomed right on through. Okay, and even though he had several atoms thick of gold foil, still most of them went right through, right through, without ever encountering a nucleus. Okay, now that gets us up to, okay, let me pause for a moment here. On page 208 in the big book, which is where this was located, this figure here, 8.5. At the top of the page is a case study, and the discovery of the electron was used, remember, was that cathode ray tube. Originally that was called a Crookes tube because English physicist named William Crookes was an early experimental electrical discharge tube, and he studied these particles. So there's another potential name for you. The oil drop experiment, and that's what J.J. Thomson used, so you'll find his name in that article. Then across the page from that, another case study, and this was the Milligan's oil, this was J.J. Thomson, and then at the end of that, you get Millikan's oil drop experiment. Okay, so this is a combination of two of these, and so that's well worth your read. Okay, then this figure here was on page 209, the same place the oil drop experiment case study was. And now we're getting into this material, the nuclear atom. There's this was said, the nucleus, that starts on page 208. The nuclear atom basically picks up there on page 209, or 8-5. Okay, now what do we mean here? Now here are some terms, and these terms are easy to get confused, so sort of get them straightened out in your mind. The atomic number, that's the number of protons in the nucleus of any atom. The number of protons in the nucleus of any atom. Okay? That determines what atom it is. If you have an atom with only one proton in it, you're guaranteed to have hydrogen. And nothing but hydrogen. Only hydrogen. Now that proton can have no neutrons in it. That's hydrogen. It can have, that proton can have one neutron with it. That's still hydrogen. It can have two neutrons with it. It's still hydrogen. What determines what an atom is how many protons it has. It can have a variety of number of neutrons, but the number of protons determines what that material is. And that's called the atomic number. How many protons are there? Okay? And elements are distinguished by their atomic number. Number 1 is always hydrogen. Number 2 is always helium. Number 3 is always, I may have said this, but lithium. Number 4 is always, I think, beryllium. Number 5 is always boron. Number 6 is always carbon. Number 7 is always nitrogen, I think. Yeah, number 8 is always oxygen. Number 9 is always, goodness gracious, what is 9? Oh, that's fluorine. And number 10 is always neon, I think it is. Okay. Go to a periodic table, just go across the rows, and you'll see 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, but you just keep the atomic numbers are there. That's how many protons are there. Right now, or when this slide was made, 113 elements were identified. If you look in your book, you'll see the number is maybe somewhere up around 118 now, or at least when the book was published. However, some of those, I'm not sure they really exist. Like the UUS and the UUO, that may be just filling in the blank. LV, though, is one that has been discovered. So maybe it's only up to, when the book was published, at 116. Okay, so maybe 3 more elements were identified after that, or maybe they don't count any of the UUs in there. Now, the number of protons always will equal the number of electrons. The protons are in the nucleus, the electrons are flying around the nucleus, and if you're in a neutral atom, a stable neutral atom, then the number of protons equals the number of electrons. So in an atom, that's the case. Now, you can have things that are not neutral, as in positively charged or negatively charged. Now, what makes it positively charged? Do you add more protons? Never! Never! You don't mess with the nucleus. The only way you get a positively charged, and what you call those are ions, is lose electrons. Because electrons are in the outer shell, you can either lose them and they become positive charged, or gain some extra ones and they become negatively charged. So that's what, if it's not a neutral atom, then it either has extra or a deficit of electrons. You never, ever, ever, ever add protons. Ever. Okay. Now, remember when I was talking about hydrogen, and I said hydrogen may be by itself one little proton, and that's all there is in the nucleus. One little electron flying somewhere all around there, never sure where it is, but it's somewhere around there. That's a stable neutral hydrogen atom. Okay? Now, however, every now and then, and maybe it's once every several hundred or 1,000 or 10,000, you'll actually find a proton with a neutron. And that makes hydrogen too, because if it's only got one proton, it's hydrogen. Okay? So you could have a neutron stuck with it. That makes what they call an isotope of hydrogen. Iso meaning same, it's the same element. But guess what? It has twice the mass, because most of the mass is in the nucleus, and if you have a neutron in there with a proton, they have almost the same mass. You've now doubled your mass, and yet you still have the same atom, because the atomic number is still 1, because there's only one proton in there. So that would be an isotope. Okay? If you have 2, now this is very, 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 very rare, but if you have 2 neutrons with 1 proton, you have 3 times the mass. 3 times the mass, but it's still an isotope of hydrogen. It's still hydrogen, because that's determined by the number of protons. Someone's trying to come in. That's Valerie is here. Okay, let me get Valerie marked here. And we've increased up to 2, 5, 6, 7. Still single digits, folks. Where, oh where are my students today? Yep, only 7 students here. Okay. All right. Valerie, we're in chapter 8. If you got the big book, we're on page 209, just about through with page 209. If you have the little book, it's 8-5. Chapter 8, the 5th page in chapter 8. We just talked about atomic number, which is the number of protons in any atom. That determines what type of atom it is, what kind of element that one's done. Every element has a fixed number of protons, and it's always the same. Okay? You can have more or less number of neutrons in that nucleus as well. That doesn't change which atom it is, but it does change its atomic mass. Not the atomic number. The atomic number is how many protons are there. The atomic mass is determined by the protons plus the neutrons. We'll get to that later. Okay? Now, here's the example, and this is also on page 209 or 8-5. Here's the ones I was talking about. The element is hydrogen. Hydrogen always has one proton. So the subscript here in front of the H is your atomic number. That's the number of protons. The mass number is the number of protons plus neutrons. This one has an atomic number of 1 and a mass number of 1. That means it has 0 neutrons. Okay? Now we're assuming here protons and neutrons have just almost the same mass, and that's the case. That's true. But if you have a atomic number of 1 but a mass number of 2, that means you have 1 proton and 1 more neutron, giving you this. And that hydrogen isotope, still hydrogen, but with a completely different mass, twice the mass of this one, that's called deuterium. Okay? Because it has twice the mass. If you have 1 atomic number of 1, that makes it hydrogen, but you have a mass number of 3, that means you've added 2 neutrons. Okay? And because it's triple the mass, they call it tritium. Tritium is very, very, very rare. Okay? But think of this. Any water molecule that is going to have either deuterium or tritium in it is going to be heavier than the other water molecules, because that hydrogen that's in that is now either deuterium or tritium. And that's going to make what they call heavy water. Okay? And heavy water is important these days because of those extra neutrons. 2 reasons nuclear power plants are built near water. Most of the time near rivers, sometimes near the ocean, but always built near water. One reason, they use water for cooling purposes. Oh, here comes Jacob. Good deal. Let me get Jacob in here before he disappears, and let me get him marked in the book. Okay. Jacob's here. He's smack in there. Okay. So that gives us up to 8 students here. And what have we got? Yep, 8 students with nobody in the waiting list, I don't think. Yep, no one in the waiting room. All right, glad you're here. Jacob, by the way, we're in chapter 8. We're just about to leave page 209 if you got a big book, or 8-5 if you got the little book. We're just talking about how an atom has 3 fundamental particles, electrons that fly around in space around it. Okay, you never can determine where they are. They're incredibly tiny. Basically, no one's measured a volume for an electron yet. They have a fixed mass, but it is incredibly small. And then in the nucleus, where all the mass lives, you have protons, which are positively charged, and neutrons, which have no charge at all. So that tiny, tiny, tiny little electron has exactly the same mass, exactly the same charge, but the opposite sign of what that massive old proton has. And then that neutron, that is bigger than either one of them, but just barely bigger than a proton, it has no charge at all. Okay, so pretty strange setup there. Okay, so let's move on to, it won't move. And these are called isotopes. When you add some neutrons to a given atomic number, which is the number of protons, keep the atomic number the same, you keep the atom, you keep the element, but now you have isotopes of that element. Okay? Now, here is a little bit more on the atomic symbols and masses. Okay, and this is basically saying almost the same thing as what we were saying before, just from a different perspective a little bit. You're going to see the same illustration. Okay, the mass number is the number of protons plus neutrons. Those electrons have so little mass we don't even count them. Okay, add up all the electrons you could possibly have in an atom and you still don't come anywhere close to what the mass of a proton or neutron is. So they don't count anything for the mass. The mass number is the number of protons plus the number of neutrons. Now, this is a difficult to me concept to explain, and it may be difficult for you to understand. The atomic mass unit, and back when I was in school they called this an AMU, atomic mass unit. Now they've gotten just to calling it a U, which I guess means a unit. The smallest unit of mass, not really, but count it as that. It's 1/12 of the carbon-12 isotope mass. Now that sounds like it's running around in circles there, and it almost is, but that is your fixed, okay? And then everything else is measured from that. So I can't tell you why they chose that, except carbon is a very common element to find in many compounds. In fact, anything organic is going to have carbon in it. And they just decided the most stable isotope there was called carbon-12, so they just took 1/12 of that mass, and that gave them what 1 unit is, 1 U is, atomic mass unit is. Now, the atomic weight is the atomic mass that we had here of an element averaged over the naturally occurring isotopes. Because if you have these other isotopes with extra neutrons in it, then your atomic weight has to account for those as well. Okay? So here's the example. Here's what we saw before. Here's your element here, hydrogen. Atomic number goes as a subscript in front. The mass number is a superscript in front. And what you do, the atomic number is how many protons. So hydrogen always has 1 proton. But the mass number is the sum of the protons plus neutrons. So for it to be 1,1 hydrogen, that means there's no neutrons because the mass number is the same as the atomic number. But a 2,1 hydrogen would be 1 neutron and 1 proton, and a 3,1 hydrogen, tritium, would be 1 proton, 2 neutrons, for a total of 3 atomic masses. Okay, so that doesn't account for the atomic weight. Let's see, the next example will. Yeah, here we have it. Now what they're going to use here is nitrogen. Nitrogen has basically 2 isotopes. The most common, nitrogen, has 7 protons and a total mass of 14, so that means 7 neutrons. Is that what you got? Very rarely, but occasionally, you'll have a 7 in 15, which means this has 8 neutrons. Okay? Now, the natural abundances here, 99.63% of all nitrogen is going to be nitrogen 14. Only barely more than 1/3% is going to be nitrogen 15. So the vast majority of these, like this is 37 out of 10,000, are going to be nitrogen 15, whereas 9,963 out of 10,000 will be nitrogen 14. So what you do, you take basically the atomic or the unit, atomic mass unit, which, and now here's what I can't explain to you. It's really complicated, but not all of them add up exactly to 14. They're always close to it, but actually this has a bit more. Now, here's part of the reason for that, and this is only part of the reason for it, just a little bit of the reason for it. Neutrons are ever so slightly more massive than protons. Just a little bit, very little. So therefore, even though we call this nitrogen 14, is actually the mass unit for this is 14.00307 atomic mass units. And whereas we call this nitrogen 15, it's actually 15.00011. So there's other things involved here too with why these don't come out exactly 14 and 15, but they're awfully close to that. Okay, and since the percentage is 0.9963, write that as a decimal number. I mean, the percentage is 99.63, write that as a decimal, 0.9963, multiply it by the atomic mass of that abundance, add that to 0.0037 times the atomic mass of this one, and that gives you nitrogen's average atomic mass is 14.0067. This was 14.007307. When you account for these, it bumps it up to 14.0067 atomic mass units. Basically what that tells you, when you look at this, you see most of nitrogen is atomic mass of 14. And sure enough it is. 99.63% of it is. Okay, that's most of it. Okay, that's what looking at the mass number will tell you. Okay, so the atomic mass is the sum basically of the neutrons plus protons. Okay, and then your fractions mostly come from the fact you will have occasionally some naturally occurring isotopes. Not all atoms have naturally occurring isotopes. Most of them do. I would say most. Many of them do. Okay, now there does come a place here. Okay, wait. I'm going to point something out to you in your book, and this is on page 210 or 8-6. These are some of the isotopes of the smallest, earliest atoms, okay, in the periodic table. The ones listed here include hydrogen, and they only list hydrogen and deuterium here. They don't list tritium, and they come up with the atomic mass. Tritium is so incredibly rare that they just didn't even put it in. Beryllium, on the other hand, only has one naturally occurring isotope, so whatever its mass compared to carbon-12. Remember, everything was compared to carbon-12. This is slightly more massive than carbon-12, so it's 9.12. Well, guess what? If it's 100% of that is the same, then it's 9.1218. Okay, now nitrogen, like we just saw, was mostly 14, occasionally a 15, rare isotope of 15. So nitrogen is going to be closer to 14, 14.0067, but that 15 in there bumps it up on the third decimal place by 3/1000ths of a atomic mass unit. Oxygen actually has 3 naturally occurring isotopes. The most common is 16, 99.759, and actually the least common is oxygen 17. And the middle common, and it's very uncommon too, is oxygen 18. It's 0.204%. Okay, so that's what, now, the fact is, oxygen 16, its atomic mass is actually 15.99491, and I cannot tell you why it's less than 16, but it's awfully close to 16. But because that's the most massive, the highest percentage one, even though the other two are more massive, they still don't have enough to pull it up to 16, but it almost is 15.9994. That's awfully close to 16. Okay? Fluorine only has one naturally occurring isotope, and that's basically fluorine 19. But again, it's a little less than that because compared to carbon 12, it's not quite on the money. Neon actually has 3 naturally occurring isotopes. Neon 20 is the most common, 90.92%. Neon 21 is about 0.257%, but neon 22 is not at all uncommon. About 9 of every 100 neon atoms will actually have 12 neutrons rather than 10. 91 out of 100 is going to have 10 neutrons, okay? And less than about 3 for every 1,000, less than 3 for every 1,000 will have 9 neutrons. Aluminum only has 1 naturally occurring isotope. Okay, so that's what that table is that I showed you. Now, there's also, at the top of this page, discovery of the nucleus. It starts off with Democritus, I guess, and then goes through J.J. Thomson and on down until you hit Ernest Rutherford. And he's the one that put the icing on the cake of what the nucleus is mostly like. Okay, then we get into atomic parts. There's a concept applied there, and that's exactly what we're talking about: protons, neutrons, electrons. So it's real worth a read there. Okay, now what they're going to talk about next here is what they mean by the classical atom. And they put atoms in quotes here. And the reason they did, and this actually has a variety of reasons this is in here, okay? It basically is leading to the case for classical atoms don't exist, okay? The way we think of them. So, from the classical theory, we have that electrons are flying around there orbiting the nucleus. That seems to be what they do. Well, if they're orbiting the nucleus, that means they've got to have a centripetal acceleration pulling them to the nucleus. Well, of course they would. Electrons are negatively charged. The protons that are in that nucleus are positively charged. The neutrons don't have any charge at all, so they're pulling them in. So that gives you a curved path. Well, a curved path means you're accelerating toward the center. Now, you're not crashing, but you're accelerating toward the center, just like the Earth is accelerating toward the sun because of its circular motion. We talked about that in, a couple chapters ago. Okay. Well, classically speaking, an accelerated charge radiates, okay? Gives off electromagnetic radiation because it's accelerated. Well, if it were to radiate, that means it's losing energy, okay? If it's losing energy, that means as it's going around the nucleus, losing energy, it's going to spiral down into the nucleus and crash. So therefore, classical atoms cannot exist. What? Okay, of course they do exist, okay? So what is the story here? Well, obviously you've got something wrong with your theory, the classical theory. Your experiment shows you atoms do exist, So that means you need a new theory. Okay? Classical theory does not account for the acceleration of electrons. So you've got to have some new theory that will provide for that. And that is where we got the quantum concept. So now we're into 8.2, which is the Bohr model. Now they haven't mentioned that yet. The slide set was set up a little differently from our text. It came along a couple of editions earlier. So here is the quantum concept. Now this was happening when all the other stuff was happening about, discovering electrons and protons and neutrons and things like that. This was happening completely, well, sort of separately from that. And one of the earliest contributors to this was a German scientist named Max Planck. Now it sort of looks like Planck, but it's Max Planck. Right around 1900, he introduced the concept of quantized energy. In other words, energy wasn't just a free-flowing substance. It came in little packets of energy. That's what we mean quanta of energies. Little packets of energy. They were quantized. And here was his formula. This is the energy of a photon of light, basically. One little packet of energy of light. The energy of that packet was proportional to the frequency of that photon, not proton, photon. Okay? The constant of proportionality was h, and this is called Planck's constant. And it is an incredibly small number. Okay? The photon frequency is small enough. You multiply it by 6.63 times 10 to the negative 34 joule seconds. Okay? Because the frequency is a per second, and this would give you something in joules, the photon energy in joules. Okay. Now, a little bit of a timeout here. Max Planck, one of the original introducers to the whole concept of quantum mechanics, very famous in Germany, and scattered throughout Germany are various Max Planck institutes. Okay? Now you might say, why am I bringing this up? Well, we have some really good German friends that live here in Birmingham. We're actually the godparents for their son, and very close to their daughter as well, and great friends. Really, some of our closest friends in Birmingham is this German couple and their two kids. Okay. Olaf's, the guy's parents, his father, worked at one of the Max Planck Institutes in Munich, Germany. So when we went over to visit with them one time, they had stayed at our house and wanted us to come visit them. We were there for meetings or something like that my wife had, and we went and stayed with them. He took us to the Max Planck Institute where he worked, where they did a lot of study of really high-level stuff. He didn't go into what he studied. He's retired from it at the time, but he took us back to that and lived just a couple of train stops away from the institute. And I believe downtown Munich there may have been another branch of that institute. Okay, now, so what? Big deal. Just happenstance. Okay. Except for the fact we also had, at one time living here, in fact, the guy was a classmate of my wife's in the School of Public Health when they were getting their doctorates. They were in the same class, and they were great buds. I mean, they bounced ideas off each other all the time, and they were really close, so we got to be close to him and his wife. His name, believe it or not, was Fabio and Rita Barboni, and my wife and I did a lot of things together. We later found out we had been married just within a few months of each other. Of course, they were in Italy and we were in U.S. Um, but anyways, we were really good friends with them. Well, when he graduated, Fabio got a job up in Boston, which please Rita no end, because she had been traveling to Boston to study English as a second language because she loved Boston and the area. And she loved Harvard and that area, okay, which is basically in Boston or very close. Well, when they were living there that year after they graduated, their son was born. So he was born in the U.S. and his name was Giacomo. Okay. And then within a year or two after he was born, Fabio's parents kept complaining and griping that he was too far away, so they moved back to Italy. But Giacomo had been born in the U.S., so he was technically a U.S. citizen. Well, fast forward now decades, okay, at least one decade, maybe a decade and a half. We went over one of those trips that my wife had meetings in Italy. We went over and visited the Barbonis there. And by this time, Giacomo was a young teenager, and he entertained us while his parents were at work or various things, and we got along splendidly. He was a lot of fun, really bright kid, a lot like his father, really, really brilliant. And when they saw how well we got along, they had already been toying with an idea. And within the next year or two, he was going to be a junior in high school. And they wanted him to come up to the U.S. and do his senior year in high school in the U.S., thinking that would give him a better shot at being able to go to a U.S. university than if he did all his schooling in Italy, and then transferring credits would be a little bit harder. So they were looking around for towns and programs and stuff where he could do his senior year in high school, and they saw how well we got along, and they said, let's ask Karen and Charles if he could come live with them and do the senior year of high school here. They found a school just up Red Mountain from where we live that would accept him. So we hosted Giacomo for a year, and it was a fun year. He got a new set of parents. We got a boy for the first time. Of course, he was a high school, but he was a great kid, really a lot of fun. And unfortunately, that was the year I had chemo, the harsh chemo for my leukemia that just happened to come in that year. But we made it through okay. And anyway, he graduated from Altamont High School and went back to Italy. In Italy, they have 5 years of high school, so he went back and did his 5th year there. So he graduated in U.S. and he graduated in Italy. So he was free to go to either school for undergrad. He came back a year later after he finished his 5th year, and we took him around to various schools, and he got a full ride scholarship to the University of North Carolina to study there. We said, take it, great school, go for it. But then he got just accepted to Harvard. And he had been born in Boston. His mother loved Boston. He had always heard about how great Harvard was and stuff like this. He couldn't pass up Harvard. He got accepted there. He wanted to go there. He basically almost drove his family in debt to do 4 years at Harvard because he didn't get a scholarship. I mean, Harvard doesn't give scholarships. They gave a little bit of a help. He did work study. He did various things. But anyway, the parents actually sold their home and moved into an apartment so they could afford his Harvard education. So anyway, when he graduated from Harvard, he went back to Italy and started grad school there. He started in Grenoble, France, but he was studying in the Max Planck Institute. That's why I got into that story. And right now he's in Munich finishing his PhD. He did his research in Grenoble, France, but he's doing his thesis or dissertation in Munich, Germany, at the Max Planck Institute. Not the research institute where our German friends' fathers worked, but at the big school in downtown Munich. So we've been surrounded by Max Planck Institute in two different ways. So anyway, there was Max Planck. Following up on him was a little guy named, what was his name? Oh, Albert Einstein, okay? In 1905, came up with the idea. Max Planck had introduced the idea that there were quantized energy packets, and Einstein said, light was made up of these quantized photons. I keep trying to say photons of energy. And basically, this is the formula you would have them. Now, the higher the frequency, the more energetic the photons are. The higher the frequency, the more energy it has. Always the constant proportionality was that constant discovered by Max Planck, Planck's constant. Very tiny, tiny, tiny little number, but very important and very consistent. Okay. Now, let's for a moment here go back and let's see if we can get some white space. We can. So I'm going to go to the whiteboard here. Don't use it much in this class because usually there's white space. Ooh, there is white space on the slide, and I'm going to erase that mark that went there. Okay, I'm going to move the whiteboard. You can't see this, but I'm doing some manipulating here because on my screen I have other things that are blocking that whiteboard. I don't think you see them, but I see them. Okay, so let me get my pen and paper here, and we'll do example 8.1 on page 211 or 8-7. Okay, and it says here, let me get the book in my lap because it's hard to read at that big of an angle. What is the energy of a photon of red light with a frequency? So why in the world is that there? Okay, the frequency, and this is the frequency of red light, so I'm going to put F sub R, is 4.60, okay, times 10 to the 14th hertz. Now there's a new unit for you. Hertz. What is a hertz? It's a cycle per second. Oops, I left off my exponent. 10 to the 14th. Okay, it's cycles per second. So this has something like 4.60 times 10 to the 14th. That would be, so 10 to the 3rd would be 1,000. 10 to the 6th would be million. 10 to the 9th would be billion. 10 to the 12th would be trillion. This would be 460 trillion cycles per second. Wow, that's really vibrating. That's its frequency. So what would be the energy of that? Well, the energy of that, E, is equal to HF. Okay, that's your formula from above, whereas Planck's constant is 6.63 times 10 to the negative 34, and that would be joule seconds okay, times, and a hertz is a per second, remember, so that's a 4.60 times 10 to the 14th per second. Okay, well, the second here cancels the per second out there. Grab your calculator. Mine is my phone. Oh, that's not there. Here it is. Okay, how are we doing on time? Got 30 minutes. I missed a phone call. Don't know when that was. I must have been downstairs. Okay, I don't recognize it anyway. Okay, pull up my calculator mode here, and in order to do scientific notation, I've got to get it in scientific calculator mode. And if you're, I think we've done this before, but let's make sure we do it. 6.63. Now don't ever type in times 10. Go for your EE key or your EXP key. On this calculator, it's the EE right there. You see where I get it to focus. There it is, EE. Okay? Press that key, EE or EXP, either one, and then type in -34. You don't type in times 10. The EE key does that for you, and do -34. But on this calculator, I have to do the number first, 34, and then do the change sign. Now, if you have a real scientific calculator, usually you'll have a key that has a negative sign in parentheses. You just hit that and then hit 34, and you have it. You don't have to do it backwards. Okay, you take that, multiply it times, and there you have 6.63. That little e stands for 10 to the minus 24, times 10 to the minus 24. Okay, multiply that by 4.6. You don't have to put that last zero in there. EE, and this is going to be 14. Okay, my writing's sort of lousy. Press equal, and what do you get? 3.0, and we got three significant digits, 3.05. If I can find my pen now, that would be approximately the energy of 3.05 times 10 to the minus 19. That's still an awfully small exponent, and that would be joules. And joule, remember, is a really small unit of energy too. So it's an incredibly small amount of energy for one photon. Okay, but of course you got many millions of billions of trillions of photons, so it does come out to a certain energy. And your book gave you 3.05 times 10 to the minus 19 joules. Okay. 8.2 says what's the energy of a photon of violet light. Okay, and violet light has a frequency of 7.30. So if I can come over here, in fact, let's do with a different color. Are y'all okay with that? That was red. I should have done that in red, but I can't get my, there we go. I don't know what's going on here. Okay, I can't get rid of that. Okay, there we go. Let's do violet. Okay, that's as close to violet as I can get. So F sub V, can y'all see that? Okay, the frequency of violet light is 7.30 times 10 to the minus times 10 to the 14 hertz, or per seconds is a better thing when you're using it. So it's the same formula. E for violet light, as opposed to this was red light, is equal to HF, and this would be violet, this was red up here. Okay, so this would be 6.63 times 10 to the minus 34 joule seconds times 4.60 times 10 to the, no, 7.30. Where's my eraser? I can get close to it, but I can't get to it. There we go. .30 times 10 to the 14th, per second. Okay, and again the second here cancels out the per second there. Pull out your handy dandy calculators again, and we'll do 6.63 EE or EXP if that's on your calculator. Negative 34, I have to type in 34, then change signs and make it negative 34, times 7.3 EE or EXP 14 equal, and this gives us the energy of 4.84 times 10 to the minus 19 joules. So significantly more energy in a violet light than there is in red light. And that's why, if you recall back when we were talking about it, ultraviolet rays are very much more harmful than infrared rays. This is red, below red is infrared, that's even lower energy. Above this is ultraviolet, higher energy, does more damage to tissue, like skin tissue, giving you skin cancers, eye tissue, destroying or damaging your, causing, oh goodness, what do you call them? I've had two of them, cataracts. Okay, it damages the lens. Okay. Any questions on that? And 4.84 times 10 to the minus 19 joules. All right. So I'm going to clear that, clear that, clear that. Okay, I'm going to put this up here for now. All right. Let's move on to back to atomic spectra. Go back to the slideshow. Okay, that was what we used, Planck's constant. We used the frequency for red light and the frequency for violet light, came up with energy for red light and energy for violet light using the same Planck's constant. Okay, so let's now look at atomic spectra. I think I'll set this aside for now and move on from here. How are we doing on time? We got some time. Okay. Now, this is another area that is a little dense, I would say. Now, for any old object out there, okay, any old object out there that absorbs and emits radiation, you could call that a black body. Okay, it gets in the way of the radiation, it absorbs it, whatever. Well, for any old thing, and especially if something that you might be heating up and it's emitting radiation, if it's just a big mixture of everything, then you have a continuous radiation distribution, and that's called a black body radiation. Okay, it depends on the temperature of the radiating object, how intense that discharge of radiation will be. That's characteristic of many solids, liquids, and very, very, very dense gases will be black body radiation, because you have such a mixture of things that are in the way. However, some materials will produce not a continuous radiation distribution, but specific line spectra. Okay, and these are emissions at characteristic frequencies. And this will be diffuse matter, not dense gases or liquids or solids that are very, very dense, but diffuse matter, and these will be what they call the incandescent gases. Now, the illustration they're going to give is the Balmer series of hydrogen lines. Okay? Now, here's kind of an example. Okay? A regular old light bulb here. Okay? Looks like an incandescent light bulb. If you send that light through a slit that only a very narrow beam. Oh, here comes Thomas. So Thomas is here today. Okay, so the top part of the alphabet is slowly filling. The middle part is doing a little bit better, and the bottom part has a few people in it, 2 out of 3. Okay, 4 in a row though in the bottom part of the middle. Okay, so you have a very narrow slit here. It happens to hit a prism. Now a prism, and it hits at an angle, and that angle, the higher energy light bends a certain amount, and the lower energy light bends a different amount. Okay, and it goes into the glass and splits into the spectrum, but then when it comes out of the glass, which is high density here, into low density air again, it reverses the process and actually bends even further. So you wind up with the high energy violet at the bottom, the low energy red at the top. And in between that you have red, orange, yellow, green, blue, and they sort of made up a color here and said indigo, okay, and then violet. Well, the main reason they did that so you could spell Roy G. Biv. As it is now, it's Roy, you know, so there wasn't a nice acronym for it. So they split up violet and called it indigo and violet, and that gave it BIV, so you could pronounce that, Roy G. Biv, as if that was somebody's name. Okay, now that would be an incandescent bulb. Okay, now we haven't gotten to the Balmer series yet, so let's see what they're illustrating next. I can't get it to advance. Okay, now this would be a tube, more than likely neon or something like this. You see this incandescent light bulb has a piece of metal in the middle of it. That's your filament, and that's giving off a whole spectra of energies. Okay, and then it's going through a gas, probably argon gas, that gives off a spectra of energy, and then going through the glass out here. That's not a lot, but you see you get almost a solid black body radiation there. But if instead of an incandescent bulb you had actually a, I want to say laser, it doesn't have to be a laser, but a single material in here, this is like a neon light or some other kind of gas in here, so everything in here is the same. It's not a metal like tungsten, it's a gas with very definite frequency. You send it through the same and you get the lines of color. This is called a line spectrum. You get one down here at the, you get a reddish one up here, a bluish one here, a violet one here, and then maybe just a combination down here. That really doesn't seem to fit what we're talking about, but the idea, you get a separated line spectrum. Okay, diffuse matter like neon gas, solid, I mean one continuous gas in there, nothing else mixing it up. Okay, now we don't have anything there. Now, where we're going to go from here, that was your line spectra. They're jumping over to Bohr's theory before they do very much more with the rules that we had. Now let me see if they even hit these rules. Not really. So let's back off, and maybe we'll do it here. They mentioned down here the Balmer series. Now, who in the world was Balmer? Okay, how are we doing on time? Yeah, we got time. Balmer was a, I just saw it and now I can't find it. Yeah, there it is. A Swiss mathematics teacher. Okay, he was studying the regularity of the spacings of the hydrogen line spectra. What we saw before was basically sort of like the neon, say, line spectra. Okay, but now let's do something with hydrogen. And they are very regularly spaced hydrogen line spectra. He was able to develop an equation that fit all of the visible lines. Okay, now how did he do it? Okay, now pull down the pad here again and do it. Here's how he came up with it, and how in the world he did this. He had a lot of time on his hand. He had 1 over the wavelength. Now that is a symbol in the Greek alphabet called a lambda, and think of that as an L, and that stands for wavelength, length as in wavelength. And 1 over lambda was equal to this number r. Now we aren't going to say what that is yet. It's a constant proportionality. Oh, here comes Tobias. And Tobias, I think, was here before and must have gotten bumped out and coming back. So welcome back, Tobias. Okay, and this is equal to r, that proportionality constant, times 1 over 2 squared, weird how he came up with this, minus 1 over n squared. Okay, where r is a constant. Now this constant here is 1.097, boy, 4 significant digits there, times 10 to the 7th. Okay, and the units here is per meter. Okay, 1 over meter. Now, what the n is, the n represents which line he was looking at. Okay, now there were 2 violet lines, so I'll put V2 and V1. For V2, the higher energy violet line, the n was equal to 6. For the lower one, n was equal to 5. For the blue-green line, so I'm just going to call this blue-green, that n was equal to 4. And for the red line, r, that n was equal to 3. Okay, and then you notice this is a 2 here. Okay, so the baseline was 2, because when you put a 2 in here, you just get 0 here, and you don't get anything else. Okay, so That's the Balmer series for the hydrogen lines. Okay. Now, if you plug in and do it, and we will do at least one of those. Okay. So let's do it. And by the way, lambda is measured in, it's a length, so that's measured in meters, and that's why this is 1/meter, because you need that to be the same unit here. This part in here has no units. These are just pure numbers. So let's do 1/n lambda here to see if we can calculate which you want to do. V2, V1, blue, green, or red. Anyone might have a choice? No? Okay. Let's do V2. N equals 6. So that will be R, which is 1.097 times 10 to the 7th per meter. Okay. Times 1/4. I can go on and square that, minus 1/36. Okay, now I can do some of that in my head, I mean on paper here. 1.097 times 10 to the 7th per meter. That's your unit. Okay. Least common denominator is 36, so this would be 9/36 minus 1/36. That would be 8/36, which would be 4/18, which would be 2/9, I believe. I'm doing that in my head, so let's see what we've got. Okay, now remember when we did the resistances in parallel and we did the reciprocal keys? We're going to be using that again. Okay, so if I can get my calculator to come on, my phone, in the calculator mode, turn it sideways because we will be using scientific notation and reciprocal keys. So it's a 1.097 EE, that's your times 10, 7, okay, times 2 divided by 9 equal, whoa, that gives you an incredibly large number, but we want the reciprocal of that, so we go over here and hit the 1/x key, and that gives you, okay, I'm going to show you the number here, a very small number. Now if we count how many zeros are going to move that, how many decimal places, going to move it 1, 2, 3, 4, 5, 6. Okay, I can't do it holding it up backwards. Let me do 1, 2, 3, 4, 5, 6, 7. Yeah, that comes up 4 point approximately. When you do the reciprocal, that would be lambda equal 4.1. I think we can do 4 significant digits. 1, 0, 2, and that would be meters. A wavelength, oh wait. There I did all the effort of counting those zeros and then forgot to write them in. That's 4.102 times 10 to the minus 7, because I moved that many places to the right, and that would be meters. Okay, now what they got, they rounded it to 4.1. I don't know why, but 4.1 meters. times 10 to the minus 7th meters. Gave you precisely the atomic spectra of the violet. This is what I call the V1 line, no, V2 line. Okay, the wavelength for the V2 line. All right, I don't think, is there anything else to do with this? That was example 8.3. No, I was just doing an example there. It says calculate the wavelength of the violet line n equals 6. We just did it in the hydrogen line spectra using, according to Balmer's equation. We just did it, and how in the world did they get it out to be 4.11? 4.10 would be better, okay? But I guess they made a mistake somewhere. Okay, now, so we did example 8.3. I didn't realize we were doing 8.3. Lucked out there. Okay. Now, I'm going to plug in my phone so I'll have plenty of charge during lab today, though I don't know that for sure I'll be needing it. I don't think I will, but I'll plug it in anyway. All right. We got 5 minutes. Let's see what we can do. That was atomic spectra. That was on page 211 or 8-7 going up to 212, 8-8. Right at the bottom of 8-8 we'll hit Bohr's theory. Okay, we probably won't be able to do it justice now, but let's get it started anyway. Now, Bohr was another character. His name was Niels Bohr, N-I-E-L-S, I believe it was. And if I'm not mistaken, he was either Norwegian, I believe Norwegian. Let's see if it shows here. It doesn't actually say, but he was another one of the great, oh, and by the way, just to let you see what these, here is the spectra for hydrogen. Yeah, there's the violet, the high level violet, second one, the blue, green, and the red. That's the hydrogen spectra according to Balmer. Well, I mean, that's what the spectra was, and his formula fit it to a T. Okay? Now, Bohr's theory had 3 rules in it. Okay? And here's what they were. Electrons only exist in certain allowed orbits. Okay? Now remember, we described electrons as being this massive cloud of electrons, but Bohr said they only exist in certain allowed orbits. Now they're not perfectly circular orbits or things like this. They have all sorts of weird shape, but that's it. Now within an orbit, an electron does not radiate. And if you remember, the problem with the classical theory is in an orbit it's accelerating and therefore it should be radiating. This says within the orbit it doesn't radiate. Now what happens though is radiation is emitted or absorbed when it changes orbits. Okay? Now let's take a fluorescent light. Now I don't have a fluorescent light in this, but if I did, what is happening there, and we've talked about this before, you have a ionized gas flying up and down that tube in both directions, and you have a material coating the tube, and the tube, that material coating the tube is a phosphorescent material. What that means is when the energy, those electrons or whatever it is flying past it, energize that and hit its just the level, it jumps up from one orbit to another orbit as it absorbs that energy. And it does it in a fixed pattern. Once that energy passes, that electron passes, or the photon of energy passes, then it falls back down again. But when it does, that same amount of energy it absorbed to jump up now is emitted, and there's your photon of a specific frequency. That's what Bohr's theory suggested. Okay, now we don't have time to get into this, so this will be where we start next time. Okay, I'm just going to make a mark somewhere here, and that's where we'll start. I probably need to talk about, well, anyway, let me take a pause here, okay? Now what I was going to say, if you go back to that last slide I was on, if I could get it to go back to it. There we go. The 3 rules, these are mentioned on page 213 or 8-9 if you have the little book. These are 3 simple little statements here. On page 213 or 8-9, the first one is called allowed orbits. That's what is mentioned right here. Okay, right here, allowed orbits, but they have a whole paragraph on that orbit. That's why I say nothing replaces reading the book. Okay, number 2 says radiationless orbits. That's when it does not radiate. Okay, so that's your number 2, but while they have that one, a longer paragraph there. And then here it says radiation is emitted or absorbed when it changes orbits. The changing of orbits is what they call quantum leaps. And there was a television show named that, but that was a completely fictional thing. So anyway, please read the book. That was on page 213. These 3 little statements here are a paragraph each over there, and some of those are pretty long paragraphs, and then it's followed by this same illustration here that we went over. Okay, so please read that. So we'll start next time with the quantum theory of the atom here, and this figure is at the top of the right hand column of page 213, and that's where we'll begin. Okay, now that done, that pretty much winds up the lecture part for today. And let's see, how did we do? We got 9 pages done in the chapter, almost 9, and we've got a total of 21. So we almost made it halfway through the chapter. Now I did a lot of extra talking there that I probably won't do next time, so we have a chance of finishing the chapter next time. But if we don't, we still have class on that 1 week from today, Tuesday. So we'll finish up the class that day if we don't finish it next time, okay, on Thursday. So we're going to close the book on that one, and what I'll do is get out of here, and let me scoot this over. I know no, you're still screen sharing. Going to close that out, and I will close, I think, this out too, if I can get it to come on. Okay, I don't think I need this anymore. Okay, let me get my diskette out of here. I don't like to leave it in there because this diskette I've used for many a year, and I'm just afraid one of these days it's going to die on me. I don't want it to be before Thursday. Okay, so let's now go to now, do any of you need me to walk you through how to get to I know I opened the slide and I don't see it now. Okay, so I'm going to have to go back down here, Word document. There it is. Okay, that's going to be the lab. Now, does anyone need me to take them through Blackboard to see where to go to get it? Okay, I was going to say, even though there's no one here that may want it, I bet you there's some people not here that probably would appreciate it. So I'm going to minimize this for a moment and go to Blackboard. Okay, I'm going to have to log into. Yes.
I got a question. Did you post any other tests after test 4?
After test 4. Now
Yeah,
that.
because I was looking, but I didn't really see enough. I seen like test 6, but like I didn't see like where the test was.
Okay, that's a very good question. I've had so many things that I've been doing over the last couple of weeks, I may have forgotten to post it. Let's see, while we're in Blackboard, we're going to look for it, okay? So here's, let me see if I can, okay, if I can get in Blackboard here. Okay, you probably can't see this. Okay, always go to Math 238. I don't know why it does that. Then it goes to that stupid stream that I don't think anyone likes. But let me then go down to this course. Whoa, stop. Okay. All right, I'm going to bring back up my Zoom. Okay, I'm going to end that for now. Okay, here we go. I'm going to do the share screen now. And that's the courses on the Google Chrome. There's my lab. Okay, so I've got both of the things I'll need. Okay, can you see my main page of Blackboard? Content page of, well, not content page. Okay, we're going to this class here. This is us. Can you all see this?
Yes.
Okay, so I'm going to click on that. All right, now let's see. Let's first. Oh, I'm in the wrong one. This is Physics 112, not Physical Science 112. Sorry about that. There we are. Nope. There we are. That's the one. Okay. Okay. Yeah, here we go. And there's our Zoom meeting today. Okay, I'm on it. Okay. Literally. And let's go to weekly activities. We're going to try to answer your first question first. So I'm going to move y'all up here. Y'all couldn't see that, but I could. And let's go down and let's see if I ever loaded. Okay, we're in week 7 now, so it may have been in week 6. Let's see if it got there. It mentions chapter 6 test. Let's see if it's there. No, they would not let me put it there. Okay, so we'll get out of chapter 6 test and get out of this and scroll back up to the top, and let's see if I put it here. All right, now there's something from Thomas and Amia and Valerie and then Jalita and Valerie. Y'all won't see all these, I see them. Okay, now there is attached is the third test. There's chapter 1 test. There's a worksheet for lab 13 and 12. Oh, I didn't know I put them here. Okay. There's the chapter 4 test, I see. I don't see it. Uh-oh, but there is a page 2. Let's see if it's over on page 2. I didn't know I had page 2. Okay. Angelia, Amia, Valerie. All course members, let's see what this one is. Chapter 2 test. No, I don't see it. I must have forgotten to load it. Okay, so let's do it now. Okay, let me go and check and find it first. Okay, this would be test 5, I believe. Yeah. Now let's see if it's here. Okay, that looks like the test. What I've got to make sure is that's all I send you. No. Okay, here's the problem, folks. And this may be why I didn't get it sent. Okay, I've got a little bit of work to do. Oh, you can't see it. It's not on screen share. Okay. What I've got to do here is do a little bit of housekeeping here. Okay. Copy. And let's go to Word. Microsoft Word. This is such a pain in the nut. Microsoft, there's Word. Blank document. We'll do a paste. Okay. Sorry, y'all probably can't see any of this, can you? Alright, they really screwed it up. I hate Microsoft. It's just such a pain in the neck product. Okay. 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 This is such a yuck. Okay. Hit the wrong key. This is why I didn't get it done before. I had too much housekeeping to do on it and I completely forgot about it. Okay. Okay, sorry to be taking our lab time to do it, but this should have been out there before. Sorry about that. Okay. Okay, was that someone trying to get in, or can y'all tell?
That was just your Windows notification.
That was what? My Windows. Go ahead, say it again.
Windows USB notification.
Okay, what does that mean?
It basically means something got unplugged on your computer.
Oh, really? I have no idea what that could have been then. Okay. Okay. I did all that and it didn't seem like that did me much good at all. Okay. This is such a pain in the neck. Or some other body part. Okay. This is part of the problem. I'm sorry, this is taking way too long. Um, I can't do all the cleanup that I need to do on it easily. Okay. Leave it like that. This is such a pain in the neck. I hate Microsoft products. They're just so awkward. Whoa. Okay. I'm getting closer, folks, believe it or not. Microsoft just screws up everything, even another Microsoft product. If it was a previous Microsoft, it messes it up. Um, and this did the same thing here. What a pain. Yuck. Okay. Now why that messed that up, I don't know. This keeps screwing up. I don't know why. Okay. This was perfectly fine a minute ago, and now it's not. Okay. I will be so happy not to have to fiddle with Microsoft anymore. Well, I do still have to, but okay. See if I can get that last question on here. I can't.
Okay. What are you trying to do, Mr. Fowler?
Okay.
Out a little bit, if I can see it on the screen.
Yeah. Let me get my screen share up there so you can see it. Right there. Okay, you can see that?
Okay, you're trying to get that last question up to the second page.
Yeah. And
can you scroll to the top of the document?
okay.
Or either, if you want to, so we want to take up time, you can send it to me and I can fix it and send it to the class.
Okay. Let me, okay. That would be probably simpler. Well, it won't take that long, will it? What were you going to suggest?
It won't take maybe 5 minutes.
Yeah. Okay, let me see. Is there something I can do right here to, that's not it. Okay. To minimize that right there. Let's see, layout, would that be it? Okay. Somewhere there's got to be margin, right? Maybe it's not layout. Is it view or home?
On your screen, because I see 2 black bars that's blocking my view of the information. So
oh, is that right? Okay. Let's see. Where in the world is...
Oh, can you click on that little thing that looks like a backwards P?
Okay. Not this thing, is it?
Down, over to your left. Oh, I can't see your cursor. Like, you see where it says ABC right there? There's a little bitty backwards P in the next little section.
ABC. I don't see an ABC.
It says ABC, ABC.
Oh, right here.
The little P, the little backwards P.
Yes, right there. Yeah, I see.
Not there.
Not there. To the right or left? Oh, that right there.
Yes.
Okay.
Okay, scroll down to the bottom of the document.
Bottom of the document. Okay. I can't get there because y'all are in the way. Okay. Now.
I'm sorry,
y'all. Okay, right there.
Okay, there's something going on with this document. I can't tell you what the problem is.
Yeah. Well, I'll know what part of it is. It was an older version and they went to a newer version. If I could just get to, I just can't remember where the thing is. The margins are. Are they under home, draw, design, layout, review, view? Is it under view? Okay. I don't see margins here under home. I don't think they're under insert.
You said you're trying to find the margins,
right? Right. Draw, I don't want draw. Design, I don't think I want design. layout.
It's under layout.
Huh? It's not layout?
It's under layout.
It is under layout. Okay. Where in the world are they here? Oh, there they are. There they are. Very first one. I see it. Okay. Let's do top.
You can do 0.5.
0.5 right there. Narrow. Let's see if that did anything.
Didn't look like it.
Okay, let me see. I got to get y'all out of the way again.
It did.
It did. I think that did it. Okay. All right. Now I want to undo that backward P because that is really ugly on my screen.
Go to the home screen.
Home screen, yeah, that's where it was, and just to the left there. So take that off. Okay, there we go. I think that will do it. Thank you.
You're welcome.
Okay. Now, I want to save this. File, save as. This PC, okay, goodness, this is so screwy. There, USB G. Okay, I'm almost there. Okay, getting closer. Okay. File name will be PHS112 test 5. Okay. I don't want it RTF. I'll put new. Now, save. All right, I think it's saved now. I got to move y'all again. Hold on. Y'all are going for a ride again. There we go. Let me go to the bottom and see if all of it's there. It is. It took up. The answer blanks are in the wrong places, but I'm not going to mess with them. Okay, y'all find them. Okay, so now what we're going to do is get out of here. Okay, get out of there. Get out of that one. And go back to PowerPoint. I mean, not PowerPoint, Blackboard. Okay, I'm under messages. I want to add a new message. Come on. Maybe it won't do it on this page because the page is full. Blackboard is so, nope. Okay, why in the world is this not responding? Okay, maybe it is now. All right. Add thing, insert local files. Okay. Test 5 new, that was today's date. No. They already had one. Let me take a look at that and see what it is. Sorry, folks. this is okay. I thought I was almost there. I already had it on the file. I just didn't look in the right place. This is so, I'm so sorry. I just wasted all that time. This I think I want to delete, but I'm not going to do it yet. Yeah, I will. I'm going to close it anyway. Okay. Now, let me go back to get out of there. This is so aggravating. Okay. Okay, can you I do all that, and now I've got all these boards right in the way. No, that's not what I want. Okay. Maybe it is. Google Chrome. Okay. Now this is what I want to move. And it's such a pain in the neck. Okay. Finally got that moved. Here we are at the messages. Okay. I've got to move y'all again. Y'all are in the way. Okay. All course message. Insert local files. And here we go. Save that. Okay. All right. Can y'all see that on your Blackboard messages now? It may take a while for it to send. I don't know. All right.
You sent it by email?
No, I sent it on Blackboard messages.
Oh, okay.
Oh yeah.
Got it?
What's this? Test 5?
Yeah. You got it?
Yeah, I see it.
I had it out there. All that things I was doing, I already had it out there. I just had dropped one letter, so I wasn't looking in the right place. Okay. So now we finally go back to, okay. Okay, so now you got test 5. Sorry you didn't have it sooner. Okay. Let's go out of messages and go back to our course. Why it got completely out of everything, I don't know. Go to weekly assignments. Can y'all see this? Can you see my Blackboard? Yes or no? Okay, so I'm trying to open weekly assignments here. There they opened finally. And let's go down to week 7. That's the week we're in. Okay, and you see instructional materials, lessons, blah, blah, blah. You see that?
Yes, sir.
Click on that. Okay, there were the PowerPoints that we've been teaching from today. And then you can go to the YouTube video playlist link back in week 1. Handouts, research paper, and locator card links back in week 1. Here is what we're going to be doing. There's the PHET, Colorado EDU. Click on that. Okay, I think I'm going to have to move y'all again. Now why, oh, this is taking a while to load, longer than it usually does. Sorry about this. I'm eating up too much class time. But the lab will go pretty quickly if we can ever get there. Why is this taking so long to load tonight? Because we're in a hurry. That's why. This is enough to drive you nuts. Okay. I'm going to eat an almond, so if you start hearing crunching, that's what's going on. Have any of you opened this? Is it opening any faster than mine?
I got it.
Okay. I wonder if I ought to cancel this and try it again. It's the right thing. It just is taking forever to load. Now, maybe I've got too many things open on my desktop. What would y'all suggest? Canceling and starting over?
I would.
Okay, here it came. As soon as you said I would, there it came. Okay, so let's go to simulations. Go to chemistry this time. Click on chemistry. And by the way, to get instructions for this, let's go back to this. Okay. I don't need that anymore. Okay. I don't need that anymore. And I don't need that anymore. Now it paused my screen sharing altogether. Let's go back to share. And where in the world? Okay. Can you see? Okay. I was going to be clever about it, but it's not doing any good. It was up here. Now, okay. It's coming back again. Now, this is what we usually see, is this kind of stuff. Man, why is it taking forever? Mostly because we're in a hurry. Let me see if I can go back here. Okay, here we go. Under instructional materials, under week 7, you'll see here is your PH111 Lab 12. Okay, if you go to the 3 dots over here, you can click on that and it will upload this. I already have it uploaded, so rather than taking time to do that, I'm going to open that, and PHET is still circling, so let's go on and get this open. New share, and this is, and remember I said there was my document. There it is. No, that's the test. So I'm going to have to go back in here. Lab 12. Okay. Close this. Go back to share. And there's Lab 12. Okay. This is what the lab looks like. Okay. And it says here, can you see this one? Go to Blackboard page for this course, go to course content, open week 7, go to instructional materials, scroll down to laboratory simulation, click on it, click on simulations, then on chemistry. That's what I did, and we're waiting. We're scrolling down to isotopes and atomic mass and click on it. So that's what we're doing next. Let's see if that ever opened. Yeah. Are you there?
Yes.
Okay. There we are. There we are. Okay. Now there's the simulation. I've got to move y'all again. Okay. This is chemistry. So let's go to isotopes and whatever I said the other word was. There it is, atomic masses. That's it. I think I have to wait till my picture shows up. Is this what you saw?
Yeah, I saw it.
Okay. Did it look like this or did it actually have a picture here?
I had the stuff. Yeah, I had the picture.
See, that's the thing. For some reason, mine is so incredibly slow. Let's see if it will open just like this. I have a feeling it won't. Well, all I'm getting is resolving host, and that indicates to me that I don't know what it indicates. Here we go. All right, isotopes and atomic mass. Go to the triangle in the circle and click on it. Okay, finally it's starting. Okay, now did I say go to mixtures? I don't think so. I think we just do isotopes. Okay, here we are. Okay, now I'm going to try to move y'all somewhere. Where do I have more room, on the left or on the right? I think I have more room on the left. So let's move y'all over here to the left. Okay, and let's go back to the lab. There it is. Let's see what to do next. Now you're in the way. Okay. Yuck. Okay. I'm going to move you back to the top. Okay. When it comes up, click on the white plus in the green square of the symbol rectangle on the right. Can y'all remember this? Wait, I have it printed out here. What am I doing? Okay. Forget that. Let's go back here and go back to here. I printed it out so I wouldn't have to go back and forth. Okay. Now, it says, when it comes up, click on the white plus sign in the green square in the symbol rectangle. Okay, so I'm going to click on that. Okay, that's what we saw in ours. What did this red number stand for? Anyone remember?
It's really hard to tell with hydrogen, though.
Yeah, it's atomic number, which is number of protons, and the upper number is atomic mass, which is the sum of the protons and neutrons. Well, since you have one proton, this shows you have no neutrons. And there it is, hydrogen with one proton in the center. Here are your neutrons down here that we're going to be adding. Okay? Then it says click on the white plus in the green square in the abundance in nature. Okay? So click on that, and hydrogen 1, this isotope here is 99.9885% abundance in nature. Okay? Select your isotope by clicking on the element and either adding or removing a neutron. Okay? Complete the following table. Get the number of protons, neutrons, and electrons from the rectangle in the upper left. Okay? Now, that's this up here. So let's do the first one. We've got hydrogen 1 right here. That's my isotope right here, hydrogen 1. Okay? How many protons does it have? 1. Okay. How many neutrons? 0. Exactly. How many electrons to be neutral? 1. It has to have the same number of electrons as protons. Is it stable?
Yes.
Yes, it is. Okay. We don't see that yet, but we'll see it when it's not. Okay. What's the mass number? 1. Okay. What is the, and there's the mass number shown here. What is the atomic mass? Okay, we go down here and click on atomic mass. And what is it? 83, okay, or whatever. Okay, you got it? Okay. What is the symbol?
H.
No, right here. Yeah, 1H.
Okay.
Just like you see right here. Okay. And what's the abundance in nature? 85%. Perfect. Perfect. You've done your first one. Okay. Does that make sense?
Yes.
Okay. Then let's go and add a neutron. Okay. So I'm going to pick up this neutron and put it in here. So there we have it. Okay. How many protons?
1.
How many neutrons?
1.
How many electrons?
1.
Okay, this is hydrogen 2, by the way. Okay. Is it stable?
Yes.
Yes, there it says stable. What's the mass number? Oh, have to go down here. Mass number?
2.
2. What's the atomic mass? Click on that one.
2.01410.
Got it. What's its symbol?
2,1H.
Perfect. And what's the abundance in nature?
0.0115%.
That's pretty small, wouldn't you say? Okay. Ready for hydrogen 3. Okay. Gonna take another neutron here and put it in the nucleus. Now, what's the number of protons?
1.
What's the number of neutrons?
2.
Number of electrons?
1.
1. Perfect. Is it stable?
No.
No. Excellent. That's all you put there is no. And what's the mass number? Wait. Yep, you're right. 3. What's the atomic mass?
3.01650. I'm sorry, 0.1605.
Got it. Okay. And the symbol?
3 to 1H. How do
Got
you
it.
say it again? I'm sorry.
Well, I mean, that's fine. 3,1H is perfectly fine, just as long as you put them in the right places. Okay. And what's the abundance in nature?
Trace.
A trace. Very, very little. Okay. We're through with hydrogen. So let's move to helium. Okay. What is the number of protons? Helium-4, by the way.
2.
2. How many neutrons?
2.
How many electrons?
2.
You're stuck on 2, aren't you? Is it stable?
Yes.
You better believe it is. Okay. Then, what's the next question? The mass number?
Mass number?
Anyone want to make a guess? 4.
4.
Okay. Atomic mass?
4.00260.
Got it. Symbol?
42HE.
Got it. Okay. And abundance in nature?
99.999.
Percent. Okay. Be sure you put percents with it. Okay. Other helium isotopes? Negligible. Okay. Now, it doesn't ask us to do it, but I'm going to see what happens if I try to put another neutron in it. Okay. It's totally unstable. It doesn't exist. abundance in nature is none. So I'm going to take that one out. That wasn't on your thing. Let's see, can we take one of these neutrons out of there? Hey, I didn't realize that. There is one, but we don't have a line for it. So that's where that other 0.0001% was there. I did not realize that. I was just doing it for fun, and there it is. So don't worry about it. I didn't give you a line for it. Okay? So through with helium. Let's go to lithium. There's lithium right there. Click on lithium right there. Click on lithium. There it goes. Okay. Now, number of protons?
3.
3 protons. You're absolutely right. Number of neutrons?
4.
4. Excellent. And this is lithium 7, by the way. Number of electrons?
3.
Perfect. Is it stable?
Yeah.
Yes. The mass number? Anyone want to make a guess?
Maybe 7.
Maybe 7, exactly. Atomic mass?
7.0160.
Perfect. And the symbol?
73Li.
Got it. Li stands for lithium. 7's its atomic mass. 3 is its atomic number. Okay. Abundance in nature?
92.71%.
That's 41%, but that's good enough.
Oh, I'm sorry.
Okay. All right. Now, notice the next one on your list. You've actually lost a proton. It goes down to lithium 6. Neutron. And that is how many protons? 3. How many neutrons?
3.
How many electrons? 3. Excellent. Is it stable?
Yes.
Yes, it is. What is the mass number? Anyone want to make a guess?
6.
6. You're absolutely right. And what's the atomic mass in AMUs?
6.01512.
Perfect. Okay. What's its symbol? What's its symbol?
6.2
Six,
Li.
6.3 Li.
Oh, yeah, I'm not.
Okay. And what's its abundance in nature?
7.59%.
7.59%. Excellent. All right. Let's go from lithium to beryllium. There, we got it. And it's beryllium 9. How many protons?
4. I'm sorry.
How many neutrons?
5.
5. How many electrons?
4.
4. Perfect. Is it stable?
Yes.
Yes, it is. Okay. Mass number. Anyone want to make a guess?
9.
9. You got it. And atomic mass?
9.01218.
Perfect. Its symbol?
94BE.
Yeah, Be stands for beryllium. And what's its abundance in nature?
100%.
Okay. That's the only beryllium we have. That's 100% of it. Let's see what happens. I'm going to try to take away a proton because it seems like an extra neutron. Let's see what happens. No, unstable doesn't exist. Well, what happened if you try to, add one back? That's what we had before, and that was stable. If you try to add another one, unstable. There is a trace of it somewhere out there in nature, but not worth, we're not going to deal with it. So let's take that back. Okay, we did beryllium. Now we go to yes, question? Okay, now we're going to boron 11. So there's your B. Click on your B. There's boron 11. How many protons? 5. How many neutrons? 6. How many electrons? 5. Perfect. Okay. Is it stable? All right. What's the mass number? Anyone want to make a guess? 11. You're right. What's the atomic mass?
11.00931.
Perfect. What's its symbol?
11.5B.
Got it. And what's its abundance in nature?
80.1%.
Wow. Now that's the lowest for the primary that we've seen. Okay. Most of them have been around 90 or 95 or 99. You know, this one's only 81. So it lets you know you probably have some isotopes. Okay. And since you have more neutrons than protons here, let's try taking away a neutron. Putting it in the neutron bowl over here. And that gives us boron 10. How many protons?
5.
How many neutrons? Say again, 5. And how many electrons? 5. Perfect. Is it stable? Yes, it is. Okay. Mass number, anyone want to make a guess? 10. You got it. Atomic mass?
10.01294.
Perfect. Okay. What's its symbol?
10.5B.
Okay. B for boron. And what's its relative abundance in nature?
19.5%.
0.9%, right?
Yes,
Okay.
19.
Got it. Okay. All right. And that accounts for all of the boron in nature. We could play around with it, and I'll let you do that if you're interested. Oh, I didn't see. Here's where it gives how many things you have up there. Okay, I didn't even notice that. Okay, so let's go to carbon. And we'll start with carbon 12. If I hit the right key. Okay, how many protons?
6.
How many neutrons?
6.
How many electrons? Y'all are stuck on 6, aren't you? Okay, is it stable? You better believe it is. That's what we base the atomic mass on, is the carbon 12 isotope. So yes, it's stable. Next is atomic mass. Anyone want to make a guess? 12. And mass number was 12. Atomic mass was exactly 12.000, because that's what we base all of them on. We base it on carbon 12. So that has to be on the nose. Okay? And the symbol?
12.6C.
Got it. And the relative abundance in nature?
98.93.
Okay. Now the next one we go to is carbon 13. Now carbon 13, let's put a neutron up there to make carbon 13. And what do we have with number of protons? Number of protons? 6. Number of neutrons?
7.
Number of electrons?
6.
6. Okay. Is it stable?
Yes.
Yes, it is. Okay. And then the mass number. Anyone want to make a guess? 13. You got it. And what's its atomic mass?
13.00335.
Got it. And what's its symbol?
13.6C.
Got it. C for carbon. And what's its relative abundance in nature?
1.07%.
Good. Very, very little, but more than some of them have been. Okay, the next one is carbon 14. Has anyone ever heard of carbon-14? Okay, before we go there, to answer that question, how many protons? 6. How many neutrons? 8. How many electrons? 6. To be neutral, it has to be. Is it stable? No. Okay. Now, what's its mass number? 14. Atomic mass?
14.00324.
Got it. Okay. And what's its symbol?
146C.
Got it. And what's its abundance in nature?
Only a trace.
Only a trace. Now, this is an important trace, though. Have any of you ever heard of carbon dating? That's sort of like Match.com. No, it isn't. That's not at all what it is. Okay. This is how they measure the age of fossils and things like that, by measuring the amount of carbon-14 found in the material. See, carbon-14 is unstable. The reason it's unstable, it's slightly radioactive, but it has a very long half-life, thousands of years. So if they go in, and how carbon-14 gets into our atmosphere in the beginning is carbon dioxide that's way up high in the atmosphere, in the ionosphere, that gets bombarded by gamma rays and other things up there, and that's what makes carbon-14. Okay, and so there's a certain amount of carbon-14 always in the atmosphere. It's such a trace that it doesn't hurt anybody that it's radioactive, because it has a very long half-life. So animals, plants, or anything else that have absorbed carbon, but then over time, thousands of years, that carbon-14 degrades away and you get less and less of it. So what they do is measure the trace amounts of carbon-14 in a fossil or in anything they're trying to date, and the amount that's in there gives them an idea how old it was. Because as long as it was living, it had the ambient amount of carbon-14. Once it died, it starts losing it because it doesn't pull any new in, and it loses it because of radioactive decay. And that's how they determine the age of fossils and dinosaur bones and all sorts of things like that. If you ever wondered, that's it, carbon-14. All right. Too much of that, wasn't there? Let's go to nitrogen. What's the first nitrogen that's listed? N14. Okay. How many protons? 7. How many neutrons?
7.
Yes. How many electrons?
7.
Yeah. You can tell the protons right here. That red 7 corresponds to these red balls. Okay. Now, is it stable?
Yes.
Yeah. Okay. Very stable. Atomic mass number. Anyone want to make a guess? 14. The atomic mass is
14.00307.
Got it. Okay. The symbol.
147N.
By the way, if you didn't want to count all those neutrons, all you have to do is subtract this number from that number, and that tells you how many neutrons. Okay?
Now you tell us the trick of the trade.
Oh, you hadn't caught that yet, huh? Okay. What's the relative abundance in nature?
99.636%.
That's pretty high, I would say, wouldn't you? Okay, the next one listed is got one more neutron. So let's take a neutron from the bowl here. I'm so glad we have a bowl of neutrons sitting around. Put it in there, and that gives you N15. How many protons? 7. How many neutrons? 8. How many electrons? 7. Okay. Is it stable?
Yes.
Yes, it is. Okay. Mass number, anyone want to make a guess? 15. Atomic mass?
15.00011.
Got it. And the symbol?
15.7N.
N stands for nitrogen. And the abundance in nature?
0.364%.
Okay, pretty small, I would say. Okay, I think we're ready for oxygen. Are you getting winded? Okay, so let's go with oxygen. How many protons? 8. How many neutrons? 8. How many electrons? Oh, excuse me, sorry. Sorry. Okay. Everybody got it? I was sneezing at the time. Okay. Is it stable?
Yes.
Yes, it is. Mass number, anyone want to make a guess? 16. That's that number right up there. Okay. And atomic mass?
15.99491.
Perfect. Okay. Symbol?
1680.
Got it. And the O stands for oxygen. And relative abundance in nature?
99.757%.
Got it. Okay. Now, in mine, I flipped over a page. Let's see if we can add a neutron. Oh, it went in. Okay. How many protons?
8.
How many neutrons?
9.
9. How many electrons? 8. Is it stable?
Yes.
Yes, it is. What's its mass number?
17.
Got it. What's its atomic mass?
16.99913.
Perfect. And the symbol?
1780.
Got it. And its abundance in nature?
0.038.
Not very much. Yes, very good. Okay. All right. It seems to indicate we might be able to add another neutron, can we? Look at that. We could. Okay. How many protons?
8.
8. How many neutrons? 10. How many electrons?
8.
8. Is it stable?
Yes.
Amazingly, it is. Okay. And actually, well, we'll get to that in a minute. What's its mass number? 18. You're absolutely right. So I didn't have to click on it, but I did. And its atomic mass?
17.99916.
Yeah, I sure didn't leave you enough room for that, did I? Okay. What's its symbol?
1880.
Got it. And its abundance in nature?
0.205%.
It's actually more abundant than 17 was, wasn't it? 17 was 0.038%. That's pretty unusual. Okay. Let's move up to fluorine. Okay. Now fluorine, what's its number of protons?
9.
What's its number of neutrons? 10. What's its number of electrons?
9.
9. Is it stable?
Yes.
Yes, it is. Good deal. What's its mass number? Make it get 19. Its atomic mass?
19.99840.
Got it. Okay, its symbol?
199F.
Got it. F is for fluorine. Okay, and what is the relative abundance in nature?
100%.
Yep. So now, it actually has more neutrons than protons, so let's take a neutron away. Okay, now that gives you F18, number of protons, still 9. The number of neutrons, 9. Number of electrons, 9. Boy, y'all are stuck on 9, aren't you? Is it stable? No, it isn't. This, I think, is the first one that when you have more neutrons than you have protons, it's stable. Fewer, before, if you had the same number, it was stable, and if you added too many, it became unstable. So this one, the same number, is unstable, which means we're getting into bigger atoms. Okay. Now, what's the, let's see, we already said the symbol, didn't we? Where were we? I got lost.
We had the mass.
Say again?
The mass number.
Oh, okay. Mass number, what you guess it is?
18.
18. And the atomic mass? 10.00094. Got it. Okay. Symbol?
189F.
Got it. And its relative abundance?
Trace.
Trace. Okay. All right. Let's move up to neon, the next of our noble gases. We'll talk about that later. Neon 20, the number of protons, number of neutrons, 10, number of electrons. Y'all are stuck on 10 again. Okay, is it stable?
Yes.
Very much so. Okay. Mass number, anyone want to make a guess?
20.
20, yeah, exactly that number there. And atomic mass?
19.99244.
Got it. Okay. Symbol?
2010 N.
Ne.
Ne.
Yeah, N would be nitrogen, Ne is neon. Okay. And the abundance in nature?
90.48%.
Okay, that means it's got about 10% of it is not that stable neon. It must be something else. And I believe we add another neutron. Let's see what happens. Oh, it went pretty well. Number of protons?
10.
Number of neutrons?
11.
11. Number of electrons?
10.
10. Okay, excellent. Is it stable?
Yes.
Yes, it is. Okay. What's its mass number? You guess?
21.
21. You got it. And atomic mass?
3.99385.
Got it. Okay. Symbol?
2110 Ne.
Got it. And its abundance in nature?
0.27%.
Wait a minute. I thought we were almost 10% short. This is only a little bit. There must be another fairly stable isotope. Let's add another neutron and see what we get. Ah, look at that. N22, Ne22, how many protons?
10.
10. How many neutrons?
12.
12. How many electrons?
10.
10. And is it stable?
Yes.
Yes, it is. Is this the first one we've had with 3 stable? I can't remember, but it's fairly unusual, it seems like. 3 stable isotopes. Where were we? Mass number. Anyone want to make a guess?
22.
22, and sure enough, that's what you get here too. And atomic mass?
21.99139.
Perfect. Okay. And its symbol?
2210 Ne.
Got it. And abundance in nature?
9.25%.
There was that almost 10%. That's where it was. Not in the next isotope, but in one that's 2 away. Okay? And unfortunately, sadly enough, that's the lab today. You want to do a few more?
Yo,
Hey.
sorry, can we go over 21?
Neon 21. Okay, let's take off one of those neutrons, and y'all can play with them too. That gives you Neon 21. Okay, that sounds like a television show or something. Okay, number of protons?
That's
10. Number of neutrons?
That's 21.
No. The difference?
11.
11. Okay. Number of electrons?
10.
10. Same as the number of protons. Okay. Is it stable?
Yes.
Yes, it is. Okay. Mass number?
21.
Got it. And the atomic mass?
20.99385.
Got it. Symbol?
2110 Ne.
Got it. And the abundance in nature?
0.27%.
Yes, very, very small. All right, good deal. Any others? Was this a worthwhile lab?
Enjoyed this one. It was good.
Okay. Now, if you want to play around with some others, let's see if it'll do anymore. Nope, it doesn't look like it goes anymore. I think we exhausted them. That's why I stopped at Neon 22. But if you wanted to try to add another neutron, you could see what happens. Oh yeah, we had already done that one, 22. How about 23? Oops, that's unstable, but it doesn't exist in nature. That would have been unstable. So you can play around with some of these. See, it doesn't register anything here either. So let's keep that from exploding by pulling that out, and now we're back to 22.
I don't think it's very responsible to leave a bowl of neutrons just lying out.
Yeah,
It's
of
just a
course.
strange matter to come across.
Yes, exactly. Okay. All right. Any questions on the lab? Okay. It's a little late now, but just would you have rather played with this on your own rather than me walking you through it?
No, you helped a lot.
Okay, well, I hope so, but I wondered if it took away from your learning. You feel like you... Okay, good deal.
I am curious which ones do explode.
None of them
Addition to the game.
Yeah, none of them explode. Those that are unstable are radioactive, though. And sometimes,
I learned how to read the neutrons and protons and electrons. Like, I didn't know how to do that. So I actually learned by you doing it.
that's what I was hoping. Thank you so much for saying that. Next lab, the one we do on Thursday, we'll be doing from the book. This will be the last one from our PHET, P-H-E-T. So bye-bye PHET. It's been fun, but we're running out of time. But the next one will be from the book, and you'll need to know how to read those things. So that's one reason I like doing this one first and showing you how to get those things. So don't forget this by Thursday, okay? Any others? Questions, issues, comments, anything? Do you want to see any of them again? All right. let me see just for sure what this says underneath here. Isotope and atomic mass, that's the name of it. Okay. Okay. What say? Time to head for the barn? Oh, we're in the barn. Okay. Any? Yeah.
But when we do when we do our next lab, it'll be some additional items we'll be adding onto our repertoire other than what we did today.
Oh yeah, it'll be stuff we talk about in class next time. We'll actually be mapping the electrons, and it's building from what we did today. We'll be doing a lot more on Thursday, and then the lab will be based on what we do in the class on Thursday. So yeah, it will be adding to the repertoire, like you said. It's just a one-page, single-page lab, but there is quite a bit to it, and we will go through it a lot like we did this. Now, what I will use, if some of you don't have books, and I think I asked this last time, if any of you did not have books and no one answered, but if you don't have a book, I will be using some of the slides from the slide set to help guide you through the lab. So hopefully we'll be able to get that done. It'll be a lot of bouncing back and forth in the slide set, but anyway, you can look at the lab now and you'll see it's out there on Blackboard, but you probably don't have enough background or information yet to fill anything out yet. But that thing's about number of protons, electrons, and neutrons, that's still going to be in the next lab too. So that's why I said, when Angelita, I think, said she understood how to do this, I said good, because we'll be using it next time as well. Okay. Any other questions, issues, concerns? You want to see anything repeated? Do you like these lab simulations?
Yes.
Okay. Okay.
I got a question.
Okay. What was the question?
Where do I turn my page in, the page where it's supposed to write?
You mean your research paper?
Yes.
Okay. You have several options. Okay. One option will be email it to me as an attachment to an email. Okay. Another option would be attach it to a Blackboard message. That would work too. Now, I don't think I've done it for this class because we're not in week 8 yet. But when we do get to week 8, one of the things I'll put in there, you know how I normally would have a lab and then possibly a test. One is called an assignment and the other was called an assessment. Well, in the week 8, I will also have a block in there. Let's see, what was it called? Yeah, it will be research paper, and but I don't have it set up that way yet. So if you want to set it in sooner, email or Blackboard message. Once that gets out there, and I'll probably do that Monday, either over the weekend or Monday, and you see it there, you can put it there. That to me is a little harder to do, but if you're used to sending things like that in Blackboard, you may find it easier to do. I don't know, but you can always send it either by email or Blackboard message.
Okay, and when is the last day of class, like the last day to turn in stuff?
Okay, that's a couple of different questions. First, the last day of class is next Tuesday. The last day of finals, or your only final day, is next Thursday. Not this day after tomorrow, but next Thursday. Because this class being a mini-term class will do, they extend one more day into finals week. However, we're going to be awfully close to finished on Thursday. If we're not finished on Thursday, we'll wrap things up on the following Tuesday. So anyway, that's it. Now, when do you turn stuff in? I know you asked for last day. Rather think in terms of the soonest day you can get it in, and that's as soon as possible. Okay, so if you can get something in tonight, get it in tonight. If it can be done tomorrow, get it in tomorrow. Thursday, Friday, Saturday, Sunday. Don't hold on to it until the last possible day. Get it in when you finish it. Okay, now that includes research paper. Last day to turn that in is next Tuesday. Okay, anything after next Tuesday and you're losing points. Okay, turn it in anytime this week, you just get your score. Okay, yesterday you'd have gotten a point. Today, no. We're in December now. Okay, your old labs, your previous tests, soon as you can get them to me, please get them to me. Gives me more time and flexibility about grading, and I don't have everything piled up at the end. It looks like it's already going to be piled up. Don't pile it any deeper. Okay, get it in as soon as you can. Okay, any other questions? Great question, by the way. Any others? Okay. One of Valerie's kids had a question, I think, but they ran on off. Okay, never mind. Okay, good deal. So ready to stop sharing? I'm sick and tired of sharing here, so that's over with. Anyone want any more questions before I end the meeting for everybody? All right, I see people leaving already, so take care, be safe. We'll see you on Thursday. All right, take care. Bye-bye.